GCE Advanced Level Chemistry Practical Series Experiment number 5. Experimental determination of molar volume of a gas. The aims of this experiment is to develop skills required to collect and measure gas volumes in the lab. So when you are carrying out experiments, certain experiments will be producing gases. So after going through this experiment, you should be able to collect gases that are produced from different experiments or different reactions, and you should be also able to measure the gas volumes that are collected. And another skill we aim to provide you with is the ability to calculate the volume of 1 mole of oxygen gas under laboratory conditions. So in this particular experiment, we are producing oxygen gas, and we aim to provide you with the necessary skills to collect the oxygen gas as well as to calculate the volume of 1 mole of oxygen gas under laboratory conditions. So let's take a look at the introduction to this experiment. Standard molar volume of a gas. Standard molar volume of a gas is the volume of 1 mole of a gas at 0 degrees Celsius temperature and 1 atm pressure. So students, we often hear the term standard molar volume of a gas. Standard molar volume of a gas. What is this standard molar volume of a gas? Standard molar volume of a gas is the volume of a given gas at 0 degrees Celsius temperature and 1 atm pressure. And these temperature and pressure conditions are known as standard temperature and pressure conditions, or often abbreviated to STP. Standard temperature and pressure conditions, often abbreviated to STP. So going forward in this experiment, whenever we use the term STP or abbreviation STP, we are referring to standard temperature and pressure conditions. Molar volume of a gas varies with temperature and pressure. So when you're talking about molar volume of a gas, or in other words, volume of 1 mole of gas, it varies with temperature as well as pressure. In this experiment, molar volume of oxygen gas is determined through a chemical reaction and then collecting the gas at usual room temperature pressure conditions. Then we will be calculating the molar volume of oxygen based on the measurements we take in the lab. Oxygen gas can be produced for the experiment using the following reaction. And the reaction is given here. We have potassium permanganate that is thermally decomposed by heating potassium permanganate solid, and it turns into potassium manganate and MnO2 and O2 gas. So in this experiment, students, the only product that is formed that is a gaseous product is oxygen gas. Out of the 3 main products that you see over here, the only product that is gaseous is oxygen. So when this particular thermal decomposition is done, we can observe the formation of oxygen gas, and we can be very sure that the only gas that is released in this experiment is oxygen. So therefore, we use this particular reaction, and there is another reason for using this reaction, and that is this particular thermal decomposition takes place at relatively lower temperatures. This thermal decomposition takes place at relatively lower temperatures, as well as it produces only one gaseous product, which happens to be oxygen. So this reaction is ideal for this experiment. in this reaction, the only gaseous product is oxygen. So as mentioned before, only gaseous product, as you can see in the given balanced chemical equation, only gaseous product is oxygen. Therefore, we can use the weight loss during the reaction to find the mass of oxygen produced. Yes, friends. So the gaseous oxygen that is produced will leave the system. So the mass of the system will go down. So the mass difference of the initial system and the final system after the reaction has taken place will give us the mass of oxygen that is produced. And through a water displacement method, we can actually collect the oxygen gas that is produced. So using the water displacement method, we can find the volume of the oxygen gas that is produced. So you will see later on a diagram of the method that we use. So through a water displacement method, we are going to measure the volume of oxygen gas that is produced. The pressure of the dry oxygen gas is given as PO2, or partial pressure of oxygen, is calculated using Dalton's law of partial pressures. Total pressure within the container that we collect the gas is going to be equal to partial pressure of oxygen plus the saturated vapor pressure of H2O. So then students, partial pressure of oxygen can be calculated using this equation. When we are carrying out this experiment, we are collecting oxygen gas on water. So there will be water here, H2O, and oxygen gas that is collected is going to be present in this compartment, and this compartment over here will be saturated with water vapor, H2O gas, as well as it is going to contain the oxygen gas that we produced. So it has O2 gas as well. So the total pressure in this region, if you call it P total pressure in this region is going to be equal to partial pressure of oxygen added with the saturated vapor pressure of water at that temperature. As you may know, at different temperatures, we have different saturated vapor pressure of water. So based on the temperature at that point, we can determine the saturated vapor pressure at that temperature. So if you know the total pressure as well as the saturated vapor pressure of water, if you know both of these values, then we'll be able to calculate partial pressure of oxygen using this equation. So it is mentioned here in this equation, P total is the atmospheric pressure and pH2O is the vapor pressure of water, which is given in the table below. So if you take a look at this table, we can see that this table lists down all of the saturated vapor pressures of oxygen at different temperatures. Temperatures ranging from 20 degrees all the way up to 100 degrees Celsius, and vapor pressures that are associated with those temperatures are given here. So majority of the time our room temperatures will range in this region, right, around 25 to let's say about 30 degrees Celsius. So we will mainly be looking at these saturated vapor pressures. After calculating the partial pressure of only the oxygen gas, we can use this combined gas law, which is represented here. So P1 V1 divided by T1 equals P2 V2 T2. So we can use this combined gas law to calculate the volume of the collected oxygen gas at standard pressure and temperature conditions. So one thing you need to understand, students, when you are carrying out this experiment and when you're collecting gas through displacement of water, uh, in the container that you collect the oxygen gas in, it is oxygen gas is present on water, meaning in the container that oxygen gas is collected to, you have both oxygen gas as well as saturated vapor of water, or in other words, water vapor as well as oxygen gas is going to be present. So the pressure of oxygen gas is not at 1 atm pressure, as well as the temperature of oxygen gas is room temperature. So usually, let's say room temperature is 25 degrees Celsius or 26 degrees Celsius. So this is not aligning well with our standard temperature and pressure conditions. One thing, standard temperature is going to be 0 degrees Celsius, but room temperature is 26 degrees Celsius. Standard pressure is 1 atm, but just a little while ago I told you the container's total pressure is equal to 1 atm, but total pressure is going to be given by two main gases. One is water vapor and the other is oxygen. So oxygen's pressure, partial pressure of oxygen, is not 1 atm. So therefore, if you are going to calculate the volume of oxygen gas at standard temperature and pressure conditions, we need to use this combined gas law. So P1 V1 T1 is going to be our laboratory conditions. P1 is going to be the partial pressure of oxygen in the container that we collected oxygen into, and V1 is going to be the volume of oxygen that we collected, and T1 is going to be the temperature at which we conducted this experiment. So P1 is partial pressure of oxygen, V1 is the volume of oxygen we collected in the lab, and T1 is the temperature at which we conducted this experiment. And then we have P2, V2 and T2. So these will represent our standard conditions. Now P2 is supposed to be the standard pressure. What is the standard pressure? 1 atm. What is the standard temperature? 0 degrees Celsius. But we will substitute the temperature here in Kelvin. So it is going to be 273 Kelvin. So pressure is 1 atm and temperature is 273 Kelvin. And at that point, only thing that we don't know is the volume. So using this combined gas law, we can calculate the volume of oxygen in standard temperature and pressure conditions. So the volume of the collected oxygen in this experiment under standard temperature and pressure conditions can be calculated using this equation. We already would know the volume of the oxygen that is collected at room temperature pressure conditions, but we need to convert it into a volume of oxygen that is collected under standard temperature and pressure conditions. So that conversion can be done using this equation. Now students, let's go through the text here, where P1, V1, T1 are STP conditions. So according to the text here, we have taken P1, V1 and T1 as the standard temperature and pressure conditions. But students, you can substitute the standard temperature and pressure conditions to either this side or to the other side. In the explanation that I gave you a little while ago, I substituted all of the standard temperature and pressure conditions onto the right hand side of the equation, where P2, V2 and T2 were considered as our standard temperature and pressure conditions. But you can consider P1, V1 and T1 as standard temperature and pressure conditions. At that point, P2, V2 and T2 would be your laboratory conditions. So P2, V2 and T2 at that point is going to be considered the partial pressure of oxygen. V2 is going to be the volume that you collected at room temperature and pressure, and T2 is going to be your temperature at which the experiment was carried out. So students, you can substitute your standard temperature and pressure conditions or your room temperature and pressure conditions onto either side, but when you are doing that, you have to keep in mind not to mix up the two conditions. For example, do not write the standard pressure along with room temperature, right? You have to use standard temperature, which is 0 degrees Celsius. So when you are substituting values, be very vigilant and be very careful not to make a careless mistake. So after substituting, since there will be only one thing that you would know in this particular equation, which is going to be our volume at standard temperature and pressure conditions, we can easily find that out by solving the equation. So all the other values will be known to you. Only unknown figure in this equation is going to be your volume at standard temperature and pressure conditions, and you can easily get to it by solving this equation. Let's take a look at some background information, students. There are several reactions that can be used or employed to produce oxygen gas through thermal decomposition. We can produce oxygen gas through thermal decomposition of metal permanganates. So we can take metal permanganates like the one that we will be using in this experiment. We are using a metal permanganate in this experiment. We'll be using potassium permanganate. So you can see potassium permanganate can be thermally decomposed to produce oxygen gas. Now this particular reaction is very suitable for our experiment, mainly for two reasons. This decomposition happens at fairly low temperatures. 190 degrees Celsius is not an extremely high temperature. This is a fairly low temperature, safe to be conducted in a lab setup. So 190 degrees Celsius temperature, and we will be producing only oxygen as the only gaseous product. So therefore, this particular reaction is ideal for our experiment that we are going to be taking a look at today. Through the thermal decomposition of metal manganetes. So metal manganetes will also decompose, right? At a high temperature, metal manganetes will also decompose to produce oxygen gas. So even if you start this reaction with metal manganate, you will also end up getting only oxygen gas as the only gaseous product. So again, one of the reasons why this first reaction is quite ideal is even the products that are formed here will not undergo further decomposition to produce any other gas. We are producing only oxygen gas even when a product of this initial reaction, which is potassium manganate. When potassium manganate undergoes decomposition, mainly three products are produced: K2O solid, MnO2 solid, as well as O2 gas. So the only gaseous product that is produced here as well is going to be oxygen. So therefore, this first reaction is quite suitable for our experiment. And we can also produce oxygen gas through thermal decomposition of metal dichromates. You can see if you take potassium dichromate, you will be producing potassium chromate, Cr2O3, and O2 gas. So over here as well, we are only producing oxygen gas as the gaseous product. Other two products are solids. However, using such a compound to produce oxygen gas could be problematic, as we have to employ really high temperatures, 500 degrees Celsius, to thermally decompose this potassium dichromate solid. So we will not be using potassium dichromate for this experiment. We can also produce oxygen gas through thermal decomposition of metal oxides, of metals that are found below copper in the reactivity series, such as Ag2O, HgO, or Au2O3. So these oxides can be thermally decomposed to produce oxygen gas and the relevant metal. Now again, we will not be using this particular compounds of our experiment here. We will be mainly using potassium permanganate. Through the thermal decomposition of metal, chlorates, bromates, and iodates, you will see whenever you heat potassium chlorates, bromates, or iodates, you will be producing oxygen gas. You can see oxygen gas is produced as the only product here. Potassium chlorates, potassium bromates, potassium iodates. When you are heating them to higher temperatures, you will be producing potassium chloride, KBr, or potassium bromide, and potassium iodide along with oxygen gas. So these reactions also can be used to produce oxygen gas. But as you may have already guessed, the temperature to which we need to subject these compounds to in order to see them undergoing a thermal decomposition is quite high. So we would not be using these compounds to carry out our experiment. Through the thermal decomposition of metal nitrates of group 1 metals. So group 1 metal nitrates. But we have one exception, lithium. Except for lithium, group 1 metals can be used or the nitrates of group 1 metals can be used to produce oxygen gas. When you heat sodium nitrate, you see sodium nitrite and oxygen is produced. Potassium nitrate, when heated, will produce potassium nitrite and oxygen gas. You can see all the other reactions here as well. Rubidium and cesium nitrates will also produce their nitrites and oxygen gas. However, the temperature required for these thermal decompositions are quite high. Seventh method is through thermal decomposition of hydrogen peroxide, H2O2. So H2O2 decomposed to produce oxygen gas as well. So this is another method that can be used to produce oxygen gas. Producing oxygen in the experiment. So we are going to have a look at some additional information about why we choose potassium permanganate for this experiment. In this experiment, we aim to produce oxygen gas through thermal decomposition of a compound. And whatever the compound that we use should undergo thermal decomposition at fairly low temperatures. So we are looking at a compound that is able to produce oxygen by undergoing thermal decomposition at a fairly low temperature. And potassium permanganate is able to undergo decomposition to produce oxygen at fairly low temperature like 190 degrees Celsius. When solid potassium permanganate is heated, it will undergo thermal decomposition and will produce O2 gas as the only gaseous product. That is very important because this experiment is designed to measure the molar volume of oxygen gas. If you have a mixture of gases produced, for example, oxygen gas and hydrogen gas, then this particular reaction will not be suitable for our experiment. However, when you are heating potassium permanganate, you only have one gaseous product produced, and that is going to be oxygen. When KMnO4 is heated, K2MnO4, potassium manganate, will be produced by this and this product will also undergo further decomposition to produce oxygen. So this is another reason why potassium permanganate decomposition is going to be quite suitable for this experiment. When you heat potassium permanganate, one of the products that is produced is potassium manganate. Potassium manganate will also undergo a thermal decomposition at a little higher temperatures, and will produce oxygen gas as the only gaseous product. There will be other solid products. However, the only gaseous product is going to be oxygen. So the thermal decomposition of potassium manganate, which was one of the products of the decomposition of potassium permanganate, will not undergo decomposition to produce a different gas. It will decompose to produce the same gas that we are looking to produce, which is oxygen. By measuring the mass difference before and after the thermal decomposition of the solid potassium permanganate, we can determine the mass of oxygen that was produced. So students, in this experiment, we are going to take a boiling tube. We are going to transfer around 5 grams of potassium permanganate, and we are going to lodge a cotton wool to the upper portion of our boiling tube. And then we are going to measure the mass of the entire setup. So boiling tube as well as our potassium permanganate and the cotton wool all together will be weighed. And we will carry out the experiment. And after we carry out the experiment, we will allow the system to cool down, and we will remove this boiling tube again, and we will reweigh the mass of the boiling tube along with its contents. So the contents will include the remaining mass of the solid and other solid products, as well as the cotton wool along with the boiling tube. So the mass of the final mass of the setup is going to be including the solid products as well as the remaining reactant and the cotton wool along with the boiling tube. So this final and initial mass difference will give us the mass of oxygen that was produced and that has left the system. So the mass of oxygen that was produced can be calculated by taking the difference between the initial mass of the setup as well as the final mass of the setup. When KMnO4 is heated, solid will undergo sublimation. This may result in mass loss if the solid gets removed from the system. To avoid this error, we will lodge a piece of cotton wool on the top of the boiling tube, which will be able to prevent KMnO4 from leaving the system. So students, we need to trap the KMnO4 that might get sublimated and might leave the system if the cotton wool is not there. So the purpose of adding a cotton wool in the upper portion of the boiling tube is to make sure that when you're heating the solid, no solid particle leaves the boiling tube. Only the oxygen gas that is produced will be leaving the system. Oxygen can diffuse through the cotton wool and only oxygen will be leaving the system, but not a single solid particle will be leaving the system this way. So this is an image of the setup we will be using. You can see we have our potassium permanganate at the bottom of the boiling tube and a piece of cotton wool lodged on the upper end of the boiling tube. So this will catch any solid particles that are trying to leave the system. When you heat it to a higher temperature, so you will see that this powdered solid particles and the sublimated solid might try to leave the system through the opening here. However, when you have a cotton wool present, it will catch those solid particles and will not allow any of the solid to leave the system. Only gaseous oxygen will be leaving the system. So this is how we will be setting up our boiling tube. Reasons behind using KMnO for solid. Thermal decomposition takes place at a lower temperature, as we saw earlier. When it comes to using potassium permanganate, the thermal decomposition of potassium permanganate took place at fairly low temperatures like 190 degrees Celsius. and oxygen produced as the only gaseous product. There are no other gaseous products produced. Only oxygen is produced when you are thermally decomposing potassium permanganate. So these are the main two reasons. Reasons behind not using potassium dichromate. Thermal decomposition of potassium dichromate takes place at a much higher temperature, around 500 degrees Celsius. So although potassium dichromate only will produce oxygen gas when it is undergoing thermal decomposition, this is not a suitable reaction as we have to use relatively high temperatures, around 500 degrees Celsius temperatures, to carry out this reaction. So it is not going to be successful when we have to employ such high temperatures. So that is why we will not be using potassium dichromate for this experiment. Reasons behind not using sodium nitrate. The sodium nitrate decomposition takes place at again a much higher temperature, around 600 degrees Celsius. Although sodium nitrate will decompose to produce sodium nitrite and oxygen gas, this decomposition will take place at much higher temperatures. As I explained earlier in the previous slides as well, when you are having really high decomposition temperatures, those types of reactions are not going to be suitable for our experiments. At the same time, if the gaseous products, or when the solid is undergoing thermal decomposition, if you produce more than one gaseous product, then at that point also those reactions will not be suitable for our experiment. We need to make sure the only gaseous product that is produced is oxygen. So let's go over the main steps of our reaction. There are a few steps to keep in mind. So these are the steps that we need to follow. Weigh about 5 grams of dry KMnO4. So we need to find dry KMnO4. That means the KMnO4 should not contain any water in it. If you have water, that will introduce errors to our calculation. So you need to find dry KMnO4, and we need to measure around 5 grams of dry KMnO4 and transfer it to a dry boiling tube. So the boiling tube also should not be containing any water in it. If you have any water, when you heat the boiling tube, apart from the oxygen gas, there will be some water vapor also produced. Insert a cotton wool plug closer to the top of the boiling tube. So we need to add a cotton wool plug closer to the top of the boiling tube as shown in the previous diagram over here. You can see we have a cotton wool plug closer to the top of the boiling tube. Measure the total weight of the boiling tube, KMnO4, and the cotton wool, and mark it down as M1. So you first measure the 5 grams of KMnO4 into the boiling tube, and then you will insert the cotton wool plug, and the overall mass of the entire setup, boiling tube, KMnO4 and cotton wool plug, will be measured after we set it up the way that they have mentioned over here. And after measuring the mass of the entire setup, we will note it down and we'll label it as M1. Set up the apparatus as shown in the above figure and gently heat the boiling tube. So we'll be using a setup like this, where you can see our boiling tube along with the potassium permanganate is heated using a heat source, and in this case we have shown a Bunsen burner, but you can use other types of heat sources as well, like a spirit burner. And then when you heat it, the oxygen gas produced will be taken through this tube A into what is known as a wolf bottle. A wolf bottle and this will allow the displacement of equivalent volume of water when gas is filling into this wolf bottle. So oxygen gas is filling in here, and an equivalent volume to the oxygen gas volume, or equivalent volume of water to the oxygen gas volume, will be displaced through tube B into our measuring cylinder or graduated cylinder here. And there needs to be a small correction in this diagram, students. So when you are connecting these tubes, the tube B should be long enough, like so that the water, it is in contact with water. The tube B should always be in contact with water on both sides, and this tube B will be filled with water throughout. The tube B will be filled with water throughout. So it will appear this way when you are carrying out your reaction. So this is the main setup that we will be using for this experiment. So what happens is, when you are heating potassium permanganate undergoing due to potassium permanganate undergoing thermal decomposition, oxygen gas will be produced. Any solid particles that are trying to leave the system will be trapped here in the cotton wool, and then oxygen gas that is produced will be taken through this tube A into the wolf bottle, and a certain volume of oxygen gas will be collected here. An equivalent volume of water to the volume of oxygen gas will be displaced through this tube B into the graduated cylinder here. So the volume of oxygen gas over here and the water that is collected over here will be equal to one another. So after setting up the apparatus as shown in the diagram below, we'll be heating the setup, and then we'll be continuing to heat the setup until a specific amount of water is displayed due to oxygen gas. So the amount of water that we are planning on displacing is somewhere around 350 to 400 cubic centimeters. So once around 400 cubic centimeters of oxygen gas is displaced, we will stop the reaction and we will move on to measuring the mass of the final system. So after we cool the entire system to room temperature, we will then move on to measuring the final mass of the boiling tube along with its contents, and that mass is going to be known as M2. Remove the rubber tube on side B when the water level of the two containers are the same. Make sure to let remaining water in tube B transferred into our measuring cylinder. Measure the volume of water displaced using the measuring cylinder. Record the room temperature and pressure. Now students, there are few very important pieces of information here. First one is, when you are measuring the final volume of water that is collected, one thing that you need to do first after the system cools down to room temperature is that water level over here in the wolf bottle as well as the water level over here in our graduated cylinder should be even. You need to make sure by moving the measuring cylinder up and down that the water levels in both the wolf bottle and the measuring cylinder is equal to one another. And keep in mind, I mentioned earlier that this tube B is filled with water and tube B is well in contact with the water inside the measuring cylinder as well as the water inside the wolf bottle. So it's a continuous column of water that is connecting the two containers here. So when you are considering two levels of water or 2 points in a liquid that is at the same level, the pressure of those 2 points are going to be the same. So we need to make sure the pressure at this particular point over here and pressure at this point over here is the same. And that is why we lift or we bring down the measuring cylinder a little bit to make sure that the water levels are equal. After that only, we will be taking the tube B out, and all of the water that is still remaining in the tube B will be transferred into our measuring cylinder. Now, you may ask, why do we have to do that? Now, when we initially started this experiment, tube B was empty, students. It didn't have any water in it. So when we started producing oxygen gas and collecting oxygen gas into this wolf bottle, at that point only, this tube B was filled with water. So whatever the water volume that is still trapped in tube B was there due to oxygen gas displacing that amount of water into tube B. So the amount of water that is still trapped in tube B is also there due to the oxygen gas that was filling up in the wolf bottle. So the volume of water in tube B should be added to the overall volume of the measuring cylinder or overall volume of water that is collected into the measuring cylinder, because this volume of water in the tube B represent a portion of the volume of oxygen gas that was collected into our wolf bottle. So now, after having a little bit of an idea about how this experiment is conducted, we can move on to the next step. Molar volume of a gas in standard temperature and pressure. So we will take a look at a little bit of theory revolving around molar volume of a gas. So molar volume of a gas is defined as the volume of a gas that is measured at standard pressure and standard temperature. Standard pressure is 1 atm. Standard temperature is 0 degrees Celsius. So standard temperature is 0 degrees Celsius, standard pressure is 1 atm. ATM stands for atmospheres. Standard molar volume of a gas is the volume of 1 mole of gas at 0 degrees Celsius and 1 atm pressure, which is also known as standard temperature and pressure conditions. The molar volume of ideal gases at STP or standard temperature and pressure conditions is going to be 22.414 decimeters cube per mole. So standard molar volume of ideal gases, or in other words, gases that behave ideally, is 22.414 decimeters cube per mole. So 1 mole of any ideal gas acquires a volume of 22.414 decimeters cube. However, when gases deviate from ideal gas conditions, the molar volume of gases will change. Now, we do know that real gases show deviation from ideal gas conditions. Real gases will show deviation from ideal gas conditions. So, due to this reason, you will observe that the molar volumes of real gases are slightly different to the molar volume calculated for ideal gases. You can see helium, nitrogen and ammonia given here. Now, helium shows a very close relationship to ideal gas molar volume. 22.41. It doesn't show a great deviation, only a slight deviation. But when it comes to nitrogen, it is 22.40 decimeters cube per mole. And when it comes to ammonia, it shows a greater deviation, which is 22.08 decimeters cube per mole. So ammonia shows a greater deviation from ideal gas behavior or ideal gas molar volume. The greater the deviation from ideal gas condition, a lower molar volume is observed. So when you deviate too far from ideal gas behavior, then molar volume is becoming smaller. So let's observe why this is. So let's take a look at molecular kinetic theory so that we can observe why deviating from ideal gas behavior will result in a smaller molar volume in real gases. The theory that attempts to explain the behavior of gases at the molecular level is known as the molecular kinetic theory. So the purpose of the molecular kinetic theory is to attempt to explain the behavior of gases at a molecular level. So this particular theory uses a few assumptions. So these are the assumptions that are given here. Gases are composed of widely separated large number of small particles. So if you consider gas molecules, or sometimes when it comes to noble gases and all that, we have atoms. So if you consider these gas molecules or gaseous atoms to be gas particles, you would notice that these gas particles occupy such a small volume, or not occupy, actually the gas particle has such a small volume. However, these gas particles are widely separated with a greater distance between them. So they end up occupying a larger volume. If you take actual gas particles, their real volume is quite small. But these gas particles, they don't stay close to one another. They are quite separated, widely separated. So they end up taking a larger volume. They end up occupying a larger volume. So we say, compared to the volume occupied by a gas, the actual volume of a gas particle is quite small, to the point where we can say it is negligible. So they are widely separated, and the actual volume of a gas particle is quite small, but since they are widely separated, they end up occupying a really large volume. So this is one of the reasons, compared to liquids and solids, gases have quite a low density, and at the same time gases are compressible, because although we say molar volume of a gas is this, we are talking about how much of a volume 1 mole of gas will occupy, not the actual volume of individual gas particles. We are talking about how much volume the gas will occupy, not just a single gas molecule's volume, right? So now when it comes to this, we can also understand why some gases are compressible, because actual gas volume is quite small, but since they are widely separated, there are so much of empty spaces in between them. So gases can be compressed. Each particle in a gas is in random, all possible directions, in random motion. In random motion in all possible directions, and it is going to be traveling in a straight line and undergoes perfectly elastic collisions with another particle or with the walls of the container. Different particles have different speeds. Now students, each particle, they keep traveling in straight line paths. However, when they collide with the container, they will bounce off of the container walls, and then again will travel in a straight line, and they will again collide with other gas particles. they will start to travel in different directions afterwards. So there will be collisions as well as these gas particles are traveling in straight line. They will have different speeds. Not all gas particles are traveling in the same speed. However, due to different speeds, they will all have different energies, different kinetic energies. But the average energy of the gas particles that are found within a sample of gas particles would not necessarily change just because they are colliding with one another. This is because we consider the collisions between gas particles and the collisions between the gas particle and the wall of the container are perfectly elastic. So we say the collisions are going to be perfectly elastic collisions. That means whenever a collision takes place, there is no energy loss. We are only transferring energy from one particle to another, or whatever the collisions that take place, there will not be any energy loss happening due to those collisions being perfectly elastic. That's another assumption we make. Let's take a look at the third point. The average kinetic energy of a gas particle depends only on the absolute temperature. So students, when you keep the volume of a container the same, and if you increase the temperature of this container where you have a sample of gas in the container, so if you increase the temperature, then what happens is, students, you will observe the pressure of this container increases. So let's say you have a container filled with a gas and you increase the temperature of this container. And then what happens? The pressure of the container increases. Why is this happening? So the pressure of a container mainly arises from gas particles that are moving at a specific velocity collides with the internal walls of the container. When you increase the temperature, due to the heat energy that is provided to the gas particles are starting to move fast. Their kinetic energy is now elevated. So now they have a higher speed. They will travel faster and collide on the container walls at a higher frequency. Due to this elevated frequency of collisions on the wall of the container, the pressure of the container increases. So students, this statement is indicative of the fact that when you increase the pressure of when you increase the temperature of a volume of gas while keeping the volume constant, the pressure of the container increases. So we can say the average kinetic energy of a gas sample is dependent only on the absolute temperature of the sample. Particles of gas behave independently of one another. The fourth point, the particles of gas behave independently from one another. This means that in an ideal condition, when you are describing ideal behavior, we assume that the gas particles are so widely separated that there are no intermolecular forces of attraction or repulsion. Between gas molecules, we assume that there are no forces of intermolecular forces of attraction or no repulsive forces present. So they are moving within the system independently from one another. That means they are not getting influenced by other gas molecules. If they have attractions, they will get influenced by it. They will not be able to be independent of other gas particles' behaviors if there are intermolecular forces of attraction, because their behavior is going to depend on the repulsive forces and the attractive forces present. However, we assume in an ideal gas behavior, we don't notice any attractions towards other gas particles or repulsive forces. So particles of a gas behaves independently of one another. The pressure of a gas arises from the sum of all the collisions of the particles with the walls of the container. So we discussed this earlier as well. So when you're talking about a gaseous system, uh, if you have a gas in a container, the pressure that is observed is due to mainly gas particles colliding with the container wall. So you might see when you take a container and if you lower the volume of the container, or if you compress the gas, you see the pressure of the gas increases. This is because now gas particles don't have to travel too far to collide with the walls of the container. Imagine you have a large container, then a gas particle should travel quite a distance to collide with the walls of the container. But if you shrink, or if you pressurize the system by reducing the volume, or when you reduce the volume, you would see the pressure of the system goes up. This is because now the gas particles don't have to travel that far to collide with the container walls. Now this means we have a higher frequency of collisions on the wall of the container, which results in a greater pressure. So the pressure of a gas depends mainly on some of the collisions. Some means all of the collisions, the total number of collisions that happen on the wall of the container. So these are the assumptions. These are the assumptions that we have in molecular kinetic theory. So ideal gases are considered to be behaving according to these assumptions. So then again, let's take a look at our real gas deviation from ideal gas behavior. So any ideal gas, students, any ideal gas adheres to PV equals nRT equation, and according to this, PV is equal to nRT. So if I take PV divided by nRT, this should be 1, right? Because PV, or this main factor that is on the left hand side of the equation, is equal to the right hand side terms. So if you take these two sides and divide by one another, it should be 1. So this is known as Z. We say compressibility factor or compressibility coefficient. So compressibility factor or compressibility coefficient of a real or of an ideal gas is 1. Compressibility factor of an ideal gas is 1. So if you keep changing the pressure of an ideal gas, students, like we have done in this particular graph, you will see that while you change the pressure of the ideal gas, the compressibility factor does not change. If a gas is behaving ideally, compressibility factor is going to be 1 at any pressure. However, you can see that when it comes to real gases do deviate slightly from this ideal gas behavior. When you keep on increasing the pressure, they do not show that their compressibility factor remains 1. Compressibility factor is not 1 anymore, it actually keeps changing. So this is a good gives a good clear picture of how much each different gas deviates from the ideal gas behavior. So according to this diagram, we can see helium deviates less than nitrogen, and ammonia is the gas that deviates the most from ideal gas behavior. So let's take a look at why that is. As seen above, in the graph, right, as seen above, the gas that shows the least deviation from the ideal gas behavior is helium, then nitrogen. The greatest deviation is seen in ammonia. Yes, we just noticed that in the previous graph. And if you take a look at the size of the molecule or the atoms, now helium is an atom, but other two are molecules. you will see the size of the molecules increase in this order. Helium atoms are small. Nitrogen atoms are quite large compared to helium atoms. And ammonia are going to be even more large, or ammonia is going to be the largest. So all three of these gases, they have London forces of attraction between the molecules. However, the size of the molecules or the atom influences the strength of these forces. Now, students, if you have studied London forces, you would know based on the size of the molecule, the number of electrons it has, the type of London force that is observed, or the strength of the London forces that are observed is going to be greater. So again, although mainly helium and nitrogen has only London forces, since nitrogen is going to be a larger molecule, if you compare the London forces of nitrogen and helium, nitrogen has more stronger London forces between the particles than helium. So we assumed that ideal gases do not have any attractions or do not have any forces of attraction between them or any repulsions. But over here in nitrogen and helium, we do know that there are forces of attraction known as London forces. Keep in mind, London forces are present in all three, but we are only taking helium and nitrogen as a comparison here because helium and nitrogen are the two gases that are only containing London forces. Ammonia, of course, contains both London forces as well as hydrogen bonds. So, the greater deviation from ideal gas behavior in nitrogen compared to helium is seen due to this reason. So, the reason is that nitrogen having a stronger London force, or nitrogen having stronger London forces of attraction compared to helium, is the reason for nitrogen to show a greater deviation from ideal gas behavior compared to helium. Now, helium's London forces are weaker. And when it comes to an ideal gas, you can't have any forces of attraction between them. Since helium has force of attraction between the helium atoms, it shows a small deviation. However, since nitrogen has London forces that are a bit more strong compared to helium's London forces, nitrogen will show a greater deviation from ideal gas behavior when compared to helium. When considering ammonia, ammonia molecules have London forces as well as hydrogen bonds. This results in a greater deviation from ideal gas behavior. As you know, hydrogen bonds are quite strong. Hydrogen bonds are quite strong, so hydrogen bonds are capable of having a very strong attraction between molecules, or creating a very strong attraction between molecules. So because of that, students, when compared to helium, nitrogen, ammonia has greater forces of attraction between molecules. Not just one type of attraction, London bonds as well as hydrogen bonds. And hydrogen bonds are much stronger than London bonds. So because of that, students, when it comes to ammonia, the deviation of ammonia when compared to an ideal gas is going to be greater. And we observe that over here. You can see ammonia gas deviates quite significantly from the ideal gas behavior. That is because the forces of attraction seen between ammonia gas molecules are much, much greater than both helium and nitrogen, as well as, of course, ideal gases. Determination of molar volume of oxygen gas. Again, we come back to the main topic. As discussed above, KMnO4 can be used to produce O2. We know that. And this is the equation for the decomposition of potassium permanganate. And we do know the potassium permanganate first will turn into potassium manganate as well as oxygen. And even the produced permanganate and even the produced manganate ions will further decompose and will produce oxygen gas. By measuring the mass difference of the initial system and the final system, we will get the mass of oxygen that was produced. So, we have mentioned here, by measuring the mass difference before and after the thermal decomposition of solid KMnO4, we can determine the mass of oxygen that was produced. This setup below can be used for the collection of oxygen gas through thermal decomposition of KMnO4. Now, I keep telling that we need to make sure that there is a connection between this container and tube B and the graduated cylinder. You should not draw the diagram in such a manner where the tube B opening lies on top or above the water level in graduated cylinder. Actually, the opening of tube B should come all the way down into the graduated cylinder, where the opening of the tube B over here should be submerged in water. It should not be above the water level. And as I mentioned earlier, this entire area will be filled with water. This entire region will be filled with water, students. So just to give you an idea, we will color it. So this entire region is filled with water. It's one continuous water column that is going to be observed in this tube. So let's take a look at what is mentioned here. When the solid in the boiling tube is heated, oxygen gas will be produced. The produced oxygen gas will travel through tube A and will get collected in the wolf bottle, which is this bottle. Now, this diagram does not do justice to the wolf bottle that you are actually going to see in the lab. So, when we are conducting the experiment, we will be using a real wolf bottle, so you will get to know what the appearance of a wolf bottle actually is like. So, a wolf bottle is a bottle that contains two openings, which will allow one tube to bring in gas into the wolf bottle, and there will be another opening that is capable of taking the water out of the bottle into a different tube. So, when the gas is getting collected to the wolf bottle, an equivalent amount of water will be displaced into a graduated cylinder through tube B. So, as you can see here, when you are producing oxygen gas, the oxygen gas will come through tube A into our wolf bottle, and wolf bottle will be completely filled. And as oxygen gas makes its way to the wolf bottle, as oxygen gas gets collected here, due to the pressure that the oxygen gas has, it will push down the water level, which will make the water travel through this tube B into our graduated cylinder. So, an equal amount of volume of oxygen gas, or equal amount of water will be displaced into this graduated cylinder when a specific amount of volume is collected in the wolf bottle. So, in simple terms, the amount of oxygen gas, or the volume of oxygen gas that is collected over here, is exactly the same as the amount of water that is going to be displaced. So, water that is displaced is the addition of volume of water that is present in this measuring cylinder, as well as the volume of water in this tube B. So, when oxygen gas gets collected here, water will get displaced into the measuring cylinder. The volume of water displaced is equal to the volume of oxygen gas collected. When about 400 cubic centimeters of water is collected to the graduated cylinder, the heat source will be removed from the boiling tube and the system is allowed to cool down to room temperature. So we allow the system to cool down to room temperature, students, after the reaction is done. Now we don't allow this reaction to run until all of the solid is completely decomposed. Instead, we have volume measurement we are going to be looking into. So if we have collected somewhere around 400 cubic centimeters of water into our graduated cylinder, at that point we will stop the reaction and we will remove the heat source from the boiling tube, and we will allow the entire system to cool down. Afterwards, the graduated cylinder will be removed, will be moved until the level in or water level, until the water level in both graduated cylinder and the wolf bottle is the same. After making sure the water levels are the same, the water remaining in the tube B is also added to the graduated cylinder. Then the volume of displaced water is measured. So students, I mentioned earlier as well that after the experiment is completed and when the system has returned to room temperature, we will move this graduated cylinder up and down until the water level in the wolf bottle as well as the graduated cylinder is even. And this water in graduated cylinder and the wolf bottle is going to be connected through tube B, and tube B is completely filled with water. So it's a continuous water column that is going to be connecting wolf bottle as well as our graduated cylinder. So when you make sure that the water levels are even, at that point, students, the pressure of water at this point and this point, because those 2 points are now at the same level, pressure of water or pressure experienced by this particular point of water is going to be the same. As you know, in a liquid, 2 points that are at the same level experience the same pressure. So we are making sure before we move on to adding what are the volume of tube B into our measuring cylinder, that we first make the pressures equal, and then after doing so we will remove the tube B, and whatever the water that is remaining in the tube B will be added to our measuring cylinder, because whatever the water that is present in the tube B was there in the first place by displacement of water. Meaning, initially when we are setting up this experiment, tube B was empty, it didn't have any water in it. So water got filled into tube B when oxygen was getting filled into wolf bottle. So some amount of water actually is going to be remaining in the tube B, which actually got filled into the tube B because oxygen got filled over here into the wolf bottle. So that means that portion of water that is still in tube B represents a portion of oxygen gas that got collected to the wolf bottle. So that is why we will be adding the water in the tube B into our graduated cylinder. The total volume of water displaced into the graduated cylinder is equal to the volume of gas that was collected into the wolf bottle. So the total volume of water that is displaced is going to be the volume of water present in the graduated cylinder plus the volume of water in the tube B. So this total displaced volume of water is equal to the volume of oxygen that was collected to our wolf bottle. So this is a diagram of making sure the 2 points are the same, and as I mentioned earlier, when you are carrying this out, the tube B should be connected to our measuring cylinder's water level, otherwise this is not going to be accurate. And then like I mentioned earlier, this entire tube should be filled with water. Actually, when you are done with the experiment, it will still be filled with water. So then, after moving this measuring cylinder up and down, we can see that point X and point Y are at the same level. At that point, you will read the volume, and then you will disconnect this tube B, and all the contents in the tube B, or the volume of water in tube B, will be transferred into our measuring cylinder, and then the volume will be measured again. So when you have made these 2 points equal to one another, we can say pressure at point X is equal to pressure at point Y. Now, pressure of point X is there due to oxygen gas as well as water vapor. Now, we are collecting oxygen gas on water. So, this entire region of this container is filled with both oxygen gas and water vapor. The water vapor is going to saturate this region. So, we can say this area is saturated with water vapor. So, the pressure of the gas, or the pressure of X, is due to mainly two things: partial pressure of water as well as partial pressure of oxygen gas that is collected. So, we will be able to find the partial pressure of water because we know at a specific temperature, when in an enclosed area, water vapor will saturate that area to produce a specific saturated vapor pressure. And for a given temperature, the saturated vapor pressures are known. And we observed that table earlier in this theory part. So, if you measure the room temperature, we'll be able to figure out the saturated vapor pressure or saturated vapor pressure of water at that particular temperature, so that you will know partial pressure of water or saturated vapor pressure of water that is seen here. And then since Px is equal to Py, we know the pressure here. So the pressure here is basically our atmospheric pressure, because this is an open system. This section is not enclosed. So therefore, it is open to the atmosphere. So the pressure of Y is going to be equal to, Py is going to be equal to pressure, or in the sense atmospheric pressure. So students, we know the atmospheric pressure, we can find out the saturated vapor pressure. So at that point, we will be able to find out the partial pressure of oxygen within this container. The total volume of water that is collected, let's say, is V cubic centimeters. Because of that, the volume of oxygen gas collected will also be the same. When the water levels in the two containers are equal, the pressure at point X and Y are also equal. This phenomenon is analogous to the principle that states pressure at 2 points within a liquid at the same level is identical. Pressure at 2 points within a liquid at the same level is identical. So when you have 2 points within the same liquid, and if these 2 points are at the same level, their pressure is identical. So because of that, we can write Px is equal to Py. Pressure at X, also known as Px, is going to be saturated vapor pressure of water, PH2O, plus partial pressure of oxygen, PO2. I mentioned this earlier. If the Px and Py are the same, and at the same time we observed when it comes to Px, in this region there are two main gases, oxygen and water vapor. So the pressure that is observed here is due to both oxygen vapor pressure, oxygen partial pressure and saturated vapor pressure, of water. So that is what we have written here. And pressure at Y is basically P, or our atmospheric pressure. Since Px is equal to Py, we can also say that saturated vapor pressure of water plus oxygen's partial pressure is equal to atmospheric pressure, what we have written here. And if you want to find out partial pressure of oxygen, that can easily be done, because we can find out the saturated vapor pressure of water by referring to the table that was given to us. So when you know the temperature of the system, you will be able to find out the saturated vapor pressure at that temperature. And atmospheric pressure was measured, and it was 760 mercury millimeters, and it does not necessarily change drastically throughout the experiment. So pressure remains a constant. The atmospheric pressure can be measured using a barometer, and the temperature can be measured using a thermometer. And we now move on to calculating the volume of oxygen gas that is collected at standard temperature and pressure. This is quite important. Now, as I mentioned earlier, using a barometer, we have measured the pressure. It is 760 mercury millimeters. And the temperature is 273 Kelvin. Now, this is the standard temperature. This is the standard pressure, right? So, standard temperature is 273 Kelvin, and standard pressure is usually 1 atm, which is equivalent to 760 mercury millimeters. So now, when we take a look at this combined gas law, as I mentioned earlier, by substituting our partial pressure of oxygen as well as the volume of oxygen collected in our lab setup, as well as the temperature at the lab environment, when you substitute these values over here to one side, it could be the P1, V1, T1 side or P2, V2, T2 side. You can use one based on your discretion. So when you substitute those three values onto one side, and onto the other side, when you substitute your standard conditions, which is the standard pressure and standard temperature, only unknown is going to be the volume at standard pressure and temperature conditions. So like you see in this part of this equation, we have substituted our partial pressure of oxygen gas as well as the volume of oxygen gas that would collected in the lab divided by the temperature of this laboratory setup. We have substituted them into P1, V1, T1. So these are lab related conditions and the measurements we obtained. And on the P2, V2, T2 side, we have our standard temperature pressure conditions substituted. So standard pressure is 760 mercury millimeters. And V2 we do not know, that is what we are trying to find out. And the temperature is 0 degrees Celsius. So we have to substitute it in Kelvin. 273 Kelvin will be substituted there. So the solution obtained for V2 in cubic centimeters will be the volume of the collected O2 gas at standard temperature and pressure conditions. So using this equation, we can calculate the volume of oxygen gas at standard temperature pressure conditions. In the lab, what we did not have the standard pressure or the standard temperature in our lab experiment setup. As we know, the pressure of oxygen gas was not 1 atm. Why? Although the total pressure in the container where the oxygen gas got collected to was 1 atm, the total pressure of that container came from both oxygen as well as water vapor. So therefore, oxygen's pressure was not 1 atm. It was only contributing towards building up 1 atm pressure. There was another contributing gas, which is water vapor. So the pressure of oxygen gas in our lab setup was not 1 atm. So we need to find out the pressure of oxygen gas that we collected. And at the same time, the temperature was not the standard temperatures. Temperature was, let's say, 26 degrees Celsius. So temperature was higher. So in the lab setup, we had oxygen collected not at the standard pressure as well as not at the standard temperature. So we need to find out the volume of oxygen gas at standard pressure and standard temperature values. So that's what we are going to be doing next. Calculate the mass of oxygen that is produced. To begin the experiment, around 5 grams of anhydrous or dry KMnO4 was carefully measured and placed into dry boiling tube, and subsequently a piece of cotton wool is securely lodged into the upper end of the boiling tube. Then the mass of the entire setup, including all of its contents, were measured, and that was labeled M1. After completing gas collection and after allowing the system to come down to room temperature, the boiling tube is reweighed, and the final mass of the boiling tube along with its contents mean remaining solid of KMnO4 and whatever the solid products that are present there, as well as the cotton wool along with the boiling tube, is measured. The difference in mass between the final measurement and the initial measurement, M1 minus M2, will represent the mass of produced oxygen. So oxygen mass produced is going to be M1 minus M2 in grams. We can determine the molar volume of oxygen by utilizing the volume and mass data acquired earlier. So earlier on, we did calculate the mass of oxygen the following way, and we did calculate the volume of oxygen gas collected at standard temperature and pressure conditions. Now, we had a room temperature volume of oxygen collected, and then we converted into the volume of oxygen collected at standard temperature and pressure conditions using combined gas law, which was V2. So we know V2 as well as the mass of oxygen. So we can write as STP, the volume of this many grams of oxygen is equal to V2. And if you multiply, or if you want to find out the volume of 32 grams. Now, why are we using 32 grams? Because the molar volume of oxygen gas is 32 grams per mole. So 1 mole of oxygen gas is equal to 32 grams. So that's why we are trying to find out what would be the volume of 32 grams of oxygen. So in order to find that volume, we have to divide V2 by the mass of oxygen that was produced, and then multiply that by 32 grams. So this is going to be the overall volume of 1 mole of oxygen gas at standard temperature and pressure conditions. So volume of 1 mole of oxygen gas at standard temperature and pressure conditions is going to be given here. Now this is in cubic centimeters still. If you convert it into cubic decimeters by multiplying with 10 to the power minus 3, you get to this value. So this expression gives us an understanding and an idea about what is going to be our calculation that will get us to our molar volume for oxygen gas. So molar volume for oxygen gas is going to contain these main parts in the expression, which is the volume of oxygen gas collected at standard temperature and pressure conditions divided by the mass of oxygen gas that was produced multiplied by 32 and 10 to the power minus 3. So this is the molar volume of oxygen gas at standard temperature and pressure conditions. So students, that actually brings us to an end in the first part of our experiment, which is going through the theory paths revolving around our experiment. I hope you have now developed a good enough understanding as to how you should be carrying out this experiment. So it is time for us to move out of the classroom and into the lab to actually conduct this experiment. So let's go ahead and move into the lab.
GCE Advanced Level Chemistry Practical Series, experiment number 5. Experimental determination of a molar volume of a gas. In this practical, we are going to produce oxygen gas through heating of potassium permanganate. And we are going to learn how to collect oxygen gas or how to collect a gas in a laboratory setup and how to measure the volume of a gas. Afterwards, using this experimental data that we gather, we are going to calculate the molar volume of a gas under laboratory conditions. Now, let's move on to the reagents and equipment we will be using for this practical. In this practical, we will be using potassium permanganate as our only reagent, and apart from that reagent, we are going to be using all of these equipment. We have here a measuring cylinder. We have here what is known as a Wolf's bottle, or sometimes referred to as wolf bottle, and we have a boiling tube. It is connected to a retort stand, and we have a spirit lamp. We have small amount of cotton wool. We have a thermometer, and we have our digital balance. In this experiment, we are going to be using this setup. Even if you take a look at your practical textbook, we have the following setup represented to you as a diagram. As mentioned in the introduction of this video, we are going to be using potassium permanganate, and we are going to heat potassium permanganate in this boiling tube that we have here with the use of our spirit burner. And when potassium permanganate is undergoing thermal decomposition, it will be producing oxygen gas. And the oxygen gas that is produced is going to be collected with the help of a wolf bottle. What we have here is referred to as wolf bottle or wolf's bottle. And when the oxygen gas produced in this boiling tube comes through this tubing that is connected to the wolf's bottle, when oxygen gas collects here, amount of water that is equivalent to the volume of the oxygen gas is going to be transferred through these tubings into our measuring cylinder. Now, this is a 1000 milliliter measuring cylinder. When we are doing this experiment, we are hoping to collect close to 400 milliliters of water, which means we are going to be collecting close to 400 milliliters of oxygen gas as well. While conducting this experiment, we will be using the following equipment as well. To measure the room temperature, we will be using a thermometer. We will be using small amount of cotton wool, and we will be using a digital balance as well. Now, let's move on to our practical. In this practical, we will be using potassium permanganate as a reagent. We will take potassium permanganate, and with the use of our digital balance here, we are going to be measuring around 5 grams of potassium permanganate, and we will transfer that into our boiling tube we have here. We can see the boiling tube is fixed onto a retort stand so that it is held in place or secured in place. And we will be heating the potassium permanganate in the boiling tube with the use of this spirit burner. When we are heating it, sometimes small solid particles can also get carried away due to the heat into this tubing. To prevent that, we will be using a small amount of cotton wool that we have here, and we'll be inserting a piece of cotton wool here to make sure that all the solid particles are entrapped in the cotton wool. And then you can see this boiling tube is connected to the apparatus that we have here. This is known as a wolf bottle. It is connected through rubber tubing, and each of the rubber tubings is connected to the boiling tube and to the wolf bottle with the help of a rubber stopper, making sure a perfect airtight seal is made with the use of a rubber stopper. So when potassium permanganate is heated, due to thermal decomposition of potassium permanganate, oxygen gas will be produced, and that oxygen gas will travel into the wolf's bottle, and when that oxygen gas is collected here, an equivalent volume to the volume of the oxygen gas that is getting collected here will get displaced into this measuring cylinder. You can see there's another tube connected to our wolf's bottle, transferring liquid into our measuring cylinder. When the reaction is taking place, we are hoping to collect around 400 milliliters of water, which means an equivalent volume of oxygen gas will be collected here in our wolf's bottle. Without further ado, let's move on to our practical. First, we have to measure 5 grams of potassium permanganate. In order to do that, we will be using our digital balance that we have here. As always, when starting off, we have to observe if the balance reads 0 and if the measurement unit is grams. So we can see the balance reads 0 and the measurement unit is grams. And then we have a dry, clean boiling tube with us. We are going to place it on our digital balance, and we are going to tear the reading of the digital balance. Now, on this balance, the mass of the boiling tube is disregarded, and to this boiling tube, now we are going to add 5 grams of potassium permanganate. We have our potassium permanganate here. Let's carefully add 5 grams of potassium permanganate into our boiling tube. So now we have measured 5.09 grams of potassium permanganate into this test tube. We need to note down the mass of potassium permanganate we have measured, and we are going to now move on to the next step, which is including a small piece of cotton wool on the upper part of our boiling tube. This will prevent any solid particles from entering the next part of the setup. Now we have placed our cotton wool around the top portion of our boiling tube. This will act as a filter, entrapping any solid particles that may try to move on to the next part of our setup. Due to the heat that is produced here, sometimes certain solid particles can get carried away into the next part of the setup if we do not have this cotton wool piece lodged on the upper end of our boiling tube. Now, after doing so, we need to again measure the entire mass of this boiling tube. When we are doing this, we have to make sure digital balance reads 0, and after making sure that it reads 0 again, we are going to place this entire boiling tube along with potassium permanganate and the cotton wool piece in it. We are going to note down the mass of the boiling tube, including the potassium permanganate and the cotton wool piece in the boiling tube. So the mass of the entire setup here is 34.40. This includes the mass of the boiling tube, potassium permanganate, and the cotton wool piece. Now, we are going to fix this boiling tube into our main setup. Now, we have included the boiling tube that we measured the mass of in the previous step in this particular setup. You can see here now that boiling tube is connected to our retort stand and is integrated into our setup. When we light this spirit burner, it will heat up the potassium permanganate that we have in the boiling tube and will produce potassium manganate, manganese dioxide, and oxygen. Out of these three products, the only gas that is produced is oxygen. So, when oxygen gas leaves this boiling tube, the overall mass of the boiling tube will be reduced. So, after the entire experiment is over, if we measure the mass of the boiling tube, we can calculate the mass of oxygen that left the system. Therefore, through a calculation, we can identify the amount of oxygen gas that was produced in grams. The oxygen gas that is produced will come and get collected into the wolf bottle. An equivalent volume of water will be displaced due to the oxygen volume that is getting collected over here in our wolf bottle. Now, let's start our experiment by lighting this spirit burner. We have started our experiment. So after a while, you will notice water is getting transferred or displaced from the wolf bottle into this measuring cylinder. You can already see water going up this glass tube and onto this rubber tube, right? Which means the reaction has already started and oxygen gas is already getting collected in this wolf bottle here. You can see water is going to be displaced onto this measuring cylinder. You can see drops of water coming into the measuring cylinder now itself. Mere seconds after starting the experiment, we can see water being collected onto our measuring cylinder. We will allow this experiment to continue until around 400 milliliters of water is collected. After that, we will stop this reaction. We will measure the atmospheric temperature and we will measure the mass of the boiling tube after the reaction has gone to completion. we have the mass of the boiling tube before we started the reaction, and then we will measure the mass of the boiling tube after we have conducted the reaction. The difference between the two will give us the mass of oxygen that is produced. And the volume of oxygen that is produced can be obtained with the help of this measuring cylinder. You can see that water is being displaced into this measuring cylinder, and the volume of displaced water is equivalent to the volume of oxygen gas that is collected here. Students, we have now removed our spirit burner from the setup. Now it is no longer used to heat up our potassium permanganate sample that we have in our boiling tube. We have collected close to 500 cubic centimeters of water through displacement of water. We are going to let the system settle down for a while, and then we'll come back and measure the volume of the water that is present in the measuring cylinder clearly. Now, we have allowed the system to cool down for a while. Before we move on to measuring the final volume of gas that is collected, I would like to bring your attention to the boiling tube that we have over here. If you focus on the boiling tube, we can see that we only included the solid over here at the bottom of the boiling tube. But as we subjected this area to heat, we can see some solid particles have started moving upwards, and it has only stopped due to a cotton wool piece that we have lodged over here. Due to the cotton wool piece we have over here, the small fine solid particles that were traveling upward did not get introduced into this tubing, meaning the solid particles remained in the boiling tube itself, and therefore it did not interfere with the weight loss that happened due to the formation of oxygen gas. So whatever the weight reduction that you will observe from this point onwards is purely due to the emission of oxygen gas from that sample. Now, let's move on to measuring the volume of oxygen gas that is produced. Before we do that, we can see over here the water that we had in the Wolf bottle has been transferred into our measuring cylinder. Before we take the final reading, we have to make sure that the two water levels in both the Wolf bottle and the measuring cylinder is equal to one another. In order to make sure that the water levels are at the same level, we have to bring the measuring cylinder closer to our Wolf bottle. We'll try to bring the measuring cylinder as close as we can to our Wolf bottle over here. Now, we have brought the measuring cylinder and the Wolf bottle close to one another, and you can see the water levels of both the apparatus is at the same level. So, at this point, we can be sure the air pressure inside the Wolf bottle is equivalent to the pressure that we have here on the surface of our measuring cylinder. On the surface of the volume of water that we have in the measuring cylinder, the pressure they experience is atmospheric pressure, so we can be sure that whatever the volume of gas that is present inside our Wolf bottle is also experiencing the same pressure. Now, all that is left for us to do is transfer the volume of water that is trapped inside this tubing. The volume of water that is trapped inside this tubing should be transferred into this measuring cylinder. You may ask why that is. That is because when we initially started this experiment, this tubing was filled with only air. Now it is filled with water, indicating when water was being displaced, some amount of water was spent in filling the volume of the tubings that we have here. That should be accounted for when it comes to calculating the volume of oxygen gas that is produced. Earlier on, they were filled with air. Now it is filled with water, which means it should be added on to our measuring cylinder over here and should be taken into account when measuring the volume of oxygen that is produced. After making sure the two water levels are at the same level, we can now remove this rubber stopper and transfer all the water that was present in the rubber tubing into our measuring cylinder. After transferring all of the water that was present in the rubber tubing into the measuring cylinder, we can now take the reading. The measuring cylinder reading is at 480 milliliters. We have collected 480 milliliters of oxygen gas here. Therefore, 480 milliliters of water was displaced into our measuring cylinder. We have the volume of oxygen gas at room temperature and 1 atm pressure. However, we still do not know the room temperature. Let's take a look at the temperature at which we conducted this experiment. We have our thermometer here. The room temperature, according to the thermometer, is 26 degrees Celsius. The room temperature, according to our thermometer, is 26 degrees Celsius. Thermometer reads 26 degrees Celsius, indicating the room temperature is 26. Afterwards, there is only one measurement to be taken, that is the mass of the measuring tube, after we have completed our reaction. So, let's take a look at our boiling tube here. Let's take out our boiling tube. As you can see, we have entrapped a lot of solid particles with the help of the cotton wool piece we lodged on the upper parts of our boiling tube. This ensures that the weight loss that happens in this boiling tube is purely due to the formation of oxygen and oxygen leaving this boiling tube. Now, let's take our digital balance. We are going to weigh the final mass of this boiling tube and its contents. We'll place it on the scale. You can see it reads 33.81 grams. So the final mass reading of this boiling tube and its contents is 33.81. So the difference of the initial mass of the boiling tube plus its contents and the final mass and its contents will give us the overall mass of oxygen that was produced. Now, we have all of our readings needed to calculate the molar volume of gas at laboratory conditions. In our next session, we are going to take a look at the calculations and the important theory parts revolving around this practical.
Welcome back to the classroom, students. So, in the first part of this experiment, we looked at the theory parts revolving around experiment number 5, which is experimental determination of molar volume of a gas. And after looking at the theory parts, after being very thorough with how we should be conducting the experiment, we went on to the lab and we conducted the experiment and we gathered the measurements that we need to calculate the molar volume of the oxygen gas. So here we are going to discuss how we can calculate the molar volume of the gas. So these are the readings we obtain in the lab. So results are given here in this table. First one is the weight of the boiling tube, and its contents before heating it, which is M1. So meaning boiling tube, KMnO4 and the cotton wool plug. The total weight of all of these three components of the system is going to be 34.40 grams. And we observe that in the lab. And after the reaction has taken place, we allow the system to cool down and then we reweighed the boiling tube and its contents. So this time around, the boiling tube contains a little bit of reactant and some solid product as well as the cotton wool. So the mass of this final system is going to be 33.81. Actually, we observed it to be 33.81. So the difference between these two masses give us the mass of oxygen that is produced. So we are currently just listing down the measurements we observed. The volume of the water that was displaced was 480 milliliters. Temperature that we measured was 26 degrees Celsius. And the pressure is atmospheric pressure. And atmospheric pressure happens to be 760 millimeters mercury or mercury millimeters. And the saturated vapor pressure of water at that particular temperature, 26 degrees Celsius temperature, that we obtained through the data table that was given to us in our practical book was 25.2 mercury millimeters. So students, we now have all of the information we need to calculate the molar volume of water. Initial mass of the system, final mass of the system, the difference of which will give us the mass of oxygen that is produced. We have the volume of oxygen that was collected, and we have the temperature of the environment that we conducted this experiment in, and we have the pressure of the atmosphere or atmospheric pressure, which is going to be 760 mercury millimeters, and we also have the saturated vapor pressure of water at the room temperature at which we conducted the experiment. So room temperature was 26 degrees Celsius and the saturated vapor pressure of water at 26 degrees Celsius is 25.2 mercury millimeters. So again, we're having a look at our experimental setup here. We have the boiling tube with KMnO4 heated, and when it is heated, oxygen gas will be produced, and oxygen gas will be collected into this wolf bottle, and it will be delivered to the wolf bottle through tube A. And to prevent any solid particles from entering this container over here, we have lodged a cotton wool piece on this area of the boiling tube. And as oxygen gas gets collected into this wolf bottle, an equal volume of water will get displaced through tube B into our measuring cylinder here. And as I mentioned earlier in the theory parts as well, you have to keep in mind that this particular tube that we have over here is connected all the way to below the water level, otherwise it is going to be inaccurate. So the water level has to be above this tube B. If the tube B is above the water level, then you would not have a continuous water column in the tube B connecting the water in these two containers. So students, when it comes to tube B should be submerged in the water in the wolf bottle as well as the water in the graduated cylinder. If it is not set up in that particular manner, the experiment is not necessarily done the correct way. So at that point, the pressure of point X is not going to be the pressure of point Y. So this is the setup that we used. So we do know pressure of point X is equal to pressure of point Y, and the pressure of point Y is equal to atmospheric pressure, and atmospheric pressure is 760 mercury millimeters. And since we know pressure at point X, over here the pressure is there due to two main gases. We have oxygen gas as well as water vapor. So since there are two gases there, the pressure experienced at point X is due to both saturated vapor pressure of water as well as partial pressure of oxygen. And partial pressure of oxygen can be calculated by Px minus PH2O, and we know Px is equal to 760 mercury millimeters. So partial pressure of oxygen is going to be 760 mercury millimeters minus the saturated vapor pressure of water at 26 degrees Celsius, which happens to be 25.2 mercury millimeters. So when you solve that, you will get to this value, which is going to be 734.8 mercury millimeters. So the saturated water pressure of water is removed from the atmospheric pressure, and the resultant value is going to be our partial pressure of oxygen. So now we have found out the partial pressure of oxygen. It is time for us to move on to calculate the oxygen gas mass, or mass of the oxygen gas produced in this experiment. So mass of oxygen gas that is produced is equal to the initial mass, which is M1, minus M2 of the boiling tube. So boiling tube with its contents initially weighed 34.40 grams, and after the experiment is completed, it weighed 33.81 grams. So the difference between the two is 0.59 grams. So the difference between the two is 0.59 grams. And the temperature of oxygen gas is 299 Kelvin. Why is this? Because we realized the temperature at which we conducted this experiment was 26 degrees Celsius. And if you convert it into Kelvin, you will have to add 26 to 273. So this value is going to be 299 Kelvin. So we have 299 Kelvin here. And pressure of just the oxygen gas that was collected, or in other words, the partial pressure of oxygen gas, happens to be 734.8. We calculated it earlier over here. So therefore, the volume, we can actually, again, we measured the volume that was collected in the lab, and the collected volume of oxygen gas was 480 cubic centimeters. So now we have the volume of oxygen gas, the pressure of oxygen gas, and the temperature of oxygen gas that was collected in the lab under laboratory conditions. So we can substitute them into our combined gas law equation. So we are going to substitute our partial pressure of oxygen into P1, and then volume of oxygen collected into V1, and temperature of oxygen into T1. So as you can see here, we are going to substitute those values here. And then standard temperature 273 degrees Celsius and standard pressure conditions are substituted into P2 and T2. Only thing that we are trying to calculate and we are currently unaware of is the V2, which is the volume of oxygen that is collected when converted into standard pressure and temperature conditions. So when you substitute all of these values and carry out the calculation, the volume of the oxygen gas at standard temperature and pressure conditions is going to be 423.73 cubic centimeters. At normal room temperature and 734.8 mercury millimeter pressure conditions, the volume of the oxygen gas is 480 cubic centimeters. But if you take the same volume of gas and observe its volume under standard temperature and pressure conditions, that volume is going to be 423.73 cubic centimeters. Now we have measured the volume of 0.59 grams of oxygen at standard temperature and pressure conditions. So we have 0.59 grams of oxygen is produced, and at standard temperature and pressure conditions we know the volume of it. Therefore, the volume of 32 grams of oxygen is going to be equal to the volume of 0.59 grams is here. We can divide by the mass of the oxygen gas that gave us this volume, which is 0.59 grams, multiplied by 32. Again, we explained this earlier in the theory part. We are multiplying this with 32 because the molar mass of oxygen gas is 32 grams per mole. So 1 mole of oxygen gas weighs 32. So since we want to figure out the volume of 1 mole of gas of oxygen, we are dividing this volume of oxygen by the mass of oxygen that gave us this volume, and then we multiply it by the mass of 1 mole of oxygen. So mass of 1 mole of oxygen is 32 grams. So you divide this volume by 0.59 grams multiplied by 32 grams. So when you do that, the volume of 1 mole of oxygen gas comes off as 22,981 cubic centimeters. 22,981 cubic centimeters. If you communicate it as the molar volume of oxygen, that is going to be communicated in decimeters cube per mole. So we need to convert this centimeters cube into decimeters cube by dividing centimeters cube value by 1,000. So the molar volume of oxygen gas is going to be 22.981 decimeters cube per mole. Now students, we do know that 0.59 grams of oxygen give us this much of volume, 423.73 cubic centimeters of volume. So we know 1 mole of oxygen weighs 32 grams. So if you know this many grams of oxygen gives us this much volume, you can try and find out how much volume is given off by 32 grams of oxygen. So that is what we are trying to do over here. Since the mass of 0.59 grams is this many cubic centimeters, how many cubic centimeters of volume would be given off by 32 grams of oxygen? Simple calculation. So when you do that, we come to realize that the volume of 32 grams of oxygen is going to be 22.981 decimeters cube or 22,981 cubic centimeters. So 32 grams of oxygen is 1 mole of oxygen. So we can write volume of 1 mole of oxygen gas is 22,981 cubic centimeters. So since molar volume is usually communicated in decimeters cube, we will divide this centimeter cube value by 1,000 to get to decimeters cubes. So the molar volume of oxygen gas is going to be 22.981 decimeters cube per mole. And the standard molar volume is communicated that way. So standard molar volume is slightly different to the experimented molar volume value. So this is the standard molar volume of oxygen, which is 22.414 decimeters cube per mole. The value that we calculated is 22.981. There's a difference between the two values. So let's take a look at the next slide and understand why there is a difference like this. The reason for differences in experimental and actual molar volume of oxygen. Deviation from ideal gas behavior in oxygen gas. Now, although we consider oxygen is an ideal gas and apply our combined gas law equation to calculate the volume of oxygen at standard temperature and pressure conditions, we do know that oxygen is deviating from ideal gas behavior. Between oxygen molecules, there are forces of attraction or intermolecular forces of attractions. So therefore, definitely, oxygen deviates from the ideal gas behavior. But we assume that it doesn't and carry out our calculations. So one reason why we do not have the same standard molar volume value observed here when we are conducting this experiment is because of the assumptions we made, such as that oxygen does not deviate from ideal gas behavior, but in fact it does. Presence of intermolecular attractions among gas molecules. Yes, oxygen does have London forces between them. So definitely this also contributes to deviate from the ideal gas behavior. So because of that, anyway, we will be seeing a deviation from the standard molar volume of oxygen when it comes to comparing the standard molar volume of oxygen and the calculated molar volume of oxygen. There will be a slight difference due to these reasons. Dissolving oxygen in water. Yes, some amount of oxygen gas will dissolve in water. This will also introduce some errors into our calculation, because not all oxygen gas is going to be present in the gaseous form if some of it dissolves in water in the Wolf bottle. System not entirely airtight. So if the system is not entirely airtight, if there are any leakages of air into the surrounding, then at that point the amount of water that is getting collected in the measuring cylinder or graduated cylinder is not correctly representing the amount of oxygen gas that got collected into the Wolf bottle. Especially if there is a small leak of oxygen gas through not having a very airtight, secure connection between different tubes or between the tube and the Wolf bottle. So if there are a certain amount of oxygen that is leaking through this system, then that amount of volume is not going to be represented in the volume that was collected to our measuring cylinder. Volume of water that was collected to the measuring cylinder will not be able to account for the amount of oxygen that got leaked through the system. So because of that, students, we will be encountering certain errors. Potassium permanganate, not completely anhydrous. So you might use potassium permanganate, KMnO4, which is not completely dry. So then what happens? When you are carrying out this experiment with potassium permanganate that has water in it, and when you are measuring the initial and the final masses of the system, you would notice a greater weight loss if there are water molecules in the system. Because when you have water in potassium permanganate, when you heat the potassium permanganate, water will evaporate and it will exit the system, and therefore it is going to be recorded as an oxygen mass that is produced. However, oxygen did not get produced here, only the water that was present in the solid got evaporated. So when you have water in potassium permanganate, that will bring an error to the calculations. So therefore, your experimental molar volume of oxygen gas as well as the standard molar volume of oxygen gas will have a difference between them. So again, having potassium permanganate that is not completely dry will introduce an error to our calculation. Errors in measuring the final volume. So when you are measuring the final volume, there can be errors. You might not bring it up to your eye level, or you might not bring your eye level down to the level of water in the graduated cylinder, or sometimes when you are transferring water from tube B into the measuring cylinder, you might not completely transfer all the water that is present in tube B. Sometimes you might forget to measure the water in tube B. So these types of measurement errors can again bring an error into your final calculations. These factors collectively contribute to the observed deviation between experimental and actual molar volume values. So in the experiment that we did, there is an error of 0.567 decimeters cube. So you can see the actual molar volume is 22.414 decimeters cube per mole, and then we have the molar volume that we calculated, which is 22.981 decimeters cube per mole. So if you take a look at these values and the difference between them, that is going to be our error. And if you want to calculate the error percentage, this 0.567 decimeters cube should be divided by the actual molar volume and multiplied by 100. So when you do that, the error percentage is given over here. The error percentage is 2.53%. Error percentage is 2.53%. So this indicates that the calculated molar volume that we have over here is not entirely accurate. It contains 2.53% of an error. Now we are going to be moving on to some questions that are revolving around experiment number 5. Let's move on to question number 1. Question number 1 says the setup below was used to measure the molar volume of oxygen. This setup below was used to measure the molar volume of oxygen. The data obtained through the experiment is given below. So this is the same setup that we were talking about earlier today. So the same exact setup that we observed in our experiment is given here in this question. The initial mass of the boiling tube with contents is equal to 32.96 grams. So initial mass of the boiling tube with its contents are 32.96 grams, and the final mass of the boiling tube was 32.40 grams. And remaining mass of the, so basically when you say final, it is going to be remaining mass of the solid plus boiling tube plus cotton wool. When you say initial mass, it is the KMnO4, boiling tube, and the cotton wool mass is given. So the temperature of the environment we carried out this experiment in is 27 degrees Celsius. Volume of water displaced is 455 cubic centimeters. And saturated vapor pressure of water at 27 degrees Celsius is given here, 26.7 mercury millimeters. So we conducted this experiment at a 27 degrees Celsius, and even the saturated vapor pressure is given to us in this question. So it is quite helpful. So the next question is, what is the volume of O2 at standard temperature and pressure conditions. So we are using potassium permanganate over here to produce oxygen gas, just like we did in our experiment. And the very first question is asking us what would be the volume of oxygen gas at standard temperature and pressure conditions. So let's first find out the following details, because we need to find out these details in order to use the combined gas law to find the volume of oxygen at standard temperature and pressure conditions. The first detail we need to know is what is the partial pressure of oxygen. So partial pressure of oxygen, PO2, this is still unknown to us. So if you go back to the question, we see over here the two levels, again making sure that this tube is in contact with the water level here. So point X and point Y are at the same level. So in a liquid, if you have 2 points that are at the same level, the pressure of those two points in the same liquid is going to be equal to one another. So we have this liquid connected through this tube B. As I mentioned several times, the tube B is also having a continuous column of water within it. So these two containers filled with water are connected through this tube B. So the tube B is not empty, students, it is filled with water. So this is the same liquid in two different containers connected through tube B. So we have 2 points of the same liquid having the same pressure. So point X pressure and point Y pressure is the same. However, container over here contains both O2 gas and water vapor, H2O gas. And since it's an enclosed area, water vapor will saturate this region. So what we see here is saturated water vapor pressure. So we can write an equation to indicate that first of all, that pressure at X is equal to pressure at Y, and measuring cylinder is open to the atmosphere, so therefore pressure at Y is equal to atmospheric pressure, which is basically 1 atm. Or in other words, we can write pressure at X is equal to pressure at Y, which is equal to atmospheric pressure 760 millimeters mercury. And then we know that pressure at X is equal to partial pressure of oxygen plus partial pressure of water vapor, or in other words, saturated vapor pressure of water. And if you want to find out partial pressure of oxygen, which we need for our combined gas law equation, we will have to subtract saturated vapor pressure of water from Px. And we know Px is equal to 760 mercury millimeters, and saturated vapor pressure at 27 degrees Celsius, which is the temperature at which we conducted this experiment. 27 degrees Celsius saturated vapor pressure is 26.7 mercury millimeters. 26.7 mercury millimeters. So the final value is 733.3. 733.3 would be our final pressure. So we were calculating pressure, not volume, students. So final pressure, or pressure of only oxygen in the container, is 733.3 mercury millimeters. So partial pressure of water is 733.3 mercury millimeters. Then we can move ahead and apply this combined gas law equation. P1 V1 is equal divided by T1 is equal to P2 V2 divided by T2. So P1 is the partial pressure of oxygen, 733.3 mercury millimeters, and then our volume is going to be, in this case, we collected, you can see the volume that was collected, 455 cubic centimeters. 455 cubic centimeters. So you can multiply this by 455 cubic centimeters divided by temperature. So the temperature that we used was 27 degrees Celsius. So we have to convert into Kelvin. 27 plus 273 will give us the Kelvin temperature value. So 27 plus 273 is 300 Kelvin. Then it's equal to P2. Now this represents our standard conditions, STP conditions. So what is the standard temperature and pressure? We'll start with pressure, 760 mercury millimeters. And V2 is the volume that we don't know about. So we are trying to find out V2 here. And the temperature is going to be, standard temperature is 273 Kelvin. Now if you are focusing on units, you can see all the units cancel off, only leaving behind cubic centimeters. You can see over here Kelvin will cancel off, mercury millimeters will cancel off, leaving behind only cubic centimeters. So your final answer will be obtained in cubic centimeters. So after substituting these values and solving the value for V2, V2 will be, you will observe this answer as well when you carry out the calculation, 399.5 cubic centimeters. So once you solve this equation, the volume of, now this is the volume of O2 gas collected at STP, standard temperature and pressure. So we didn't collect the O2 gas at standard temperature and pressure, but we can calculate if we collected the oxygen gas in standard temperature and pressure, what will be the volume, and that's what we did. We calculated if you collect this same amount of oxygen at standard temperature and pressure, what will be the volume? 399.5 cubic centimeters. You can see the volume has reduced. Obviously, when this temperature is decreased, you see a small decrease in volume as well. So this is our answer to the volume of oxygen, which is the question that they have asked here. So the question that they have asked here, what is the volume of oxygen gas at standard temperature and pressure conditions? So the answer is 399.5 cubic centimeters. This is our answer for the question that is asked. Now we move on to the second one. What is the molar volume of oxygen at STP conditions, standard temperature and pressure conditions? So again, we do know the mass of oxygen that was produced. Now how do we know? Because in the question, they have given us the initial mass of the boiling tube with contents and the final mass of the boiling tube with the contents. So these two masses, and if you take their differences, what you see is the mass of oxygen that was produced. So 32.96 and 32.40. Is equal to M1 minus M2. 32.96 minus 32.40. And this is in grams. So we have 0.56 grams of oxygen, 0.56 grams of oxygen are produced here in this particular experiment. So when you know the mass of oxygen that is produced, you can calculate the volume of oxygen that will be there if you take 32 grams of oxygen, or in other words, 1 mole of oxygen. So we can write 0.56 grams of oxygen has this volume. So we can write volume of, we write that way, volume of 0.56 grams of oxygen is equal to, and in standard temperature and pressure conditions, is equal to 399.5 cubic centimeters, because molar volume, students, is by definition is going to be the volume of 1 mole of gas under standard temperature and pressure conditions. So what we wrote here should have this condition at STP. So at standard temperature and pressure conditions, the volume of 0.56 grams of oxygen is this much. Mass of 1 mole of oxygen gas is equal to 32 grams. So therefore, volume of 32 grams of oxygen at STP, standard temperature and pressure, can be calculated. So the volume of 0.56 grams was 399.5 cubic centimeters, and this was seen in 0.56 grams. So if you multiply this by mass of 1 mole of oxygen, which is 32 grams, you get to the volume of 1 mole of oxygen at standard temperature and pressure conditions. So the volume is going to be, again, you can see very clearly, grams and grams cancel off. 22,828 cubic centimeters would be the answer. So when you divide 399.5 by 0.56 grams and multiply it with 32, you will eventually get to this volume. So this volume is the volume of 1 mole of oxygen. So this is the volume of 1 mole of oxygen. So we can actually calculate the molar volume of oxygen now. So we can write molar volume of O2 gas Now, students, when you say molar volume, it is understood that molar volume is communicated uh, in standard temperature and pressure conditions. So therefore, you don't need to write STP once more here. We did calculate the volume of oxygen gas here of 1 mole of oxygen at STP. It is mentioned in the calculation. So over here, when you are writing it as a molar volume, you have one more thing to do, that is you need to divide this value by 1000 and convert cubic centimeters into decimeters cube. So when you do that, the value would be 22.828 cubic decimeters, because cubic centimeters will not be used in molar volume. We will communicate it in cubic decimeters per mole, which means for a single mole of oxygen, the volume would be 22.828 decimeters cube. So this will be our molar volume, students. This will be our molar volume. So now we have calculated the answer to that part of the question as well. So the question asks, what is the molar volume of oxygen? Molar volume of oxygen is going to be 22.828 decimeters cube per mole. Right, so now we can move on to the next part. The expected molar volume was 22.414 decimeters cube per mole, was not observed. So this is the expected molar volume. We learned in our theory part that expected molar volume of a gas is 22.414. We did not observe this. They're asking for the reasons. Give reasons for not obtaining the actual value of this molar volume or standard molar volume of a gas. Oxygen deviates from ideal gas behavior. Oxygen deviates from ideal gas behavior. Oxygen has intermolecular forces. And at the same time, we do know that the system or the setup might not be completely airtight. We also know that the potassium permanganate KMnO4 measured might not be completely dry. And we also do know that there can be errors in measurements. There can be errors in measurements, mass measurements, volume measurements. There can be errors. So these are some of the errors that are associated with this experiment, leading us to a deviation from the standard molar volume. When you are calculating the molar volume experimentally, there can be deviation from the standard molar volume and the experimental molar volume. This small deviation is observed due to some of these errors that are mentioned here. Can the balance equation for the thermal decomposition of potassium permanganate be used for the calculation of oxygen gas that is produced if the mass of KMnO4 used is known? Now, students, we do know the balance equation for thermal decomposition of potassium permanganate. So imagine you take a specific mass of potassium permanganate and we try to decompose it until it no longer decomposes. And then will we be able to find out the mass of oxygen that way if you do know the thermal decomposition of only potassium permanganate? So the answer to that question would be no. Potassium permanganate will decompose to produce potassium manganate, manganese dioxide, and oxygen. So students, both potassium manganate and manganese dioxide can actually further undergo thermal decomposition at high temperature and produce oxygen gas. So just knowing this first equation where potassium permanganate undergoes decomposition will not allow us to determine the mass of oxygen that is produced. So first let's take a look at the equation for potassium permanganate decomposition. So we have KMnO4. It will decompose to produce K2MnO4 plus MnO2 plus O2. Now, potassium manganate is a solid. This is a solid as well, and oxygen is produced as a gas. Now you can see if it is balanced. You can see on both ends the number of potassiums are balanced. There's two manganese atoms here, and you can see two of them here as well. And the number of oxygens on the right hand side is 8. Number of oxygens on the left hand side here is also 8. So if you know just this equation, you will not be able to determine the mass of oxygen gas. Why? Because these two products that are produced, they are also capable of undergoing thermal decomposition at higher temperature. Right? So they undergo thermal decomposition. So you can't just use this equation alone to get to the mass of oxygen that was produced through the thermal decomposition of potassium permanganate. Instead, we usually use the method that we used in the experiment that we did in the lab. Instead of using equations, we will be using the actual mass difference. Because even when these two products undergo further thermal decomposition, they also produce only oxygen as the gaseous product. Right? There are other products, solid products that they produce. However, the only gaseous product that they produce is oxygen gas. We can take a look at those reactions as well. So you will be producing this K2O plus MnO2 plus O2. So now students, as you can see, when you write this equation, it is not balanced. So we'll have to balance it. So if you add 2 here, you will have to add a 2 here. And then you'll see the potassiums are balanced. But the manganese is not balanced, so we'll have to add 2 in front of MnO2. So now the manganese is balanced. You can see there are 2 manganese on the left hand side and the 2 on the right hand side. Oxygen, there are 8 oxygen atoms on the left hand side, but on the right hand side we have 4 plus 2, 6. Again, 6 plus 2 is 8. So the number of oxygens are also balanced. And we need to make sure to indicate that we are heating this to obtain these products, and we need to include their state symbols as well, because it is important in this case to identify that the only gaseous product produced here is oxygen. Other products are going to be solid products. So this is what happens when potassium manganate or K2MnO4 undergoes decomposition. What about MnO2 undergoing decomposition? So MnO2 undergoes decomposition to produce Mn3O4 and oxygen. Mn3O4 and oxygen. Again, you would notice that this equation is not balanced. There are 3 Mn's here. So I need to add a 3 in front of MnO2. So when I do that, number of oxygens on the left hand side becomes 6, but the number of oxygens on the right hand side is 4 plus 2 is 6. So number of oxygens are also completely balanced. And we will indicate the state symbols. So we know that when you are heating the MnO2 solid, it can decompose to Mn3O4 solid and oxygen gas. So these are the reactions that take place if you continuously provide heat, not only to decompose our potassium permanganate, but also to decompose the rest of the products that are produced. And in this particular reaction, all of these two solid products that are produced will also undergo decomposition in the following way to produce oxygen gas. So students, just knowing this equation alone will not allow us to calculate the mass of oxygen that is going to be produced. So the answer would be, for this question, we will not be able to produce due to the following reason. This reaction will produce oxygen gas as well as two other solid products that can undergo further decomposition to produce the same gas in question, which is oxygen gas. So therefore, we can't use only this balanced equation to determine the mass of oxygen that was produced when decomposing potassium permanganate thermally. So after discussing this question now, we can move on to the next one. What is the reason for lodging a piece of cotton wool in the boiling tube when when the experiment is carried out? So students, when you were observing the reaction that is in the lab, that we did in the lab, you might have noticed we only included when we only added the solid into the bottom of the boiling tube. However, when the experiment was going on, we can see that the entire inner surface of the boiling tube is covered with this dark purple black color solid. So why is this? When you are providing heat to potassium permanganate, a portion of potassium permanganate can undergo sublimation, so certain solid particles also can get carried away out of the boiling tube. So to prevent this solid particles being taken away from the boiling tube, we will lodge a cotton wool on the upper area of the boiling tube so that only gas or only oxygen gas produced can pass through the cotton wool and get collected in the wolf bottle. So students, the reason for that would be to prevent any solid particles from exiting the system. So that is the main purpose of the cotton wool plug. You can also mention that potassium permanganate can undergo sublimation and some solid particles can get carried away and can exit the boiling tube. And to prevent this situation, we will add a cotton wool plug. And I can ask another question. How do you usually identify that some amount of potassium permanganate has gotten out of the boiling tube. If you don't have the cotton wool plugs securely positioned within the boiling tube, some potassium permanganate might somehow come out of the boiling tube and into tube A. And then the tube A is connected to our wolf bottle that has water in it. So some amount of potassium permanganate, if it ever exits the boiling tube, will come out of the tube A into the wolf bottle filled with water. And when potassium permanganate dissolves in wolf bottle, what happens? Wolf bottle or water in the wolf bottle will turn to a purple color. So then later on, when the wolf bottle water gets displaced into the measuring cylinder, the water there will also turn to a purple color. So having a color change, such as clear water turning into purple color, is going to be an indication that some amount of potassium permanganate has exit the system. Some amount of potassium permanganate has managed to exit the system, and when this happens, students, when you are measuring the final mass of boiling tube and its remaining content, the final mass reading is going to be error sum, because we are going to measure the mass of oxygen gas produced by the mass difference of the initial and the final mass of the boiling tube. So if some amount of potassium permanganate has managed to go out of the boiling tube, then that particular mass loss is going to be recorded in our calculation as a oxygen mass that is produced. So we lost some potassium permanganate mass, however, we are going to be considering that as a mass of oxygen that got produced. So again, this will bring an error to your calculation. So you do not want any potassium permanganate to exit the system that way. We only want the potassium permanganate to remain within the boiling tube and undergo thermal decomposition. If it ever exits the boiling tube, then the final mass reading will be affected by this, or final mass measurement will be affected by this, and therefore the final calculation of molar volume of oxygen will also be affected. Then we move on to the next question. The volume of carbon dioxide collected by downward displacement of water method by thermal decomposition of 8.4 grams of magnesium carbonate is given here, which is 2.37 decimeters cube. The temperature of the system after it is cooled down was 27 degrees Celsius. The pressure was 1 atm and the saturated vapor pressure at 27 degrees Celsius was 26.7 mercury millimeters. Write the balanced chemical equation for the thermal decomposition of magnesium carbonate. Write the balanced chemical equation for thermal decomposition of magnesium carbonate. So we have magnesium carbonate solid. I am quite certain that all of you are familiar with this type of very simple thermal decomposition equations. So you have magnesium oxide solid and carbon dioxide produced, CO2. Right, students. So this is the equation, and equation is already balanced. You don't need to put in a lot of effort into balancing this. This is the equation that is easily balanced. So magnesium carbonate turns into magnesium oxide and carbon dioxide. So this is the answer to the first question. So the second part of the same question, calculate the number of moles of carbon dioxide gas produced if the entire magnesium carbonate mass used has undergone complete thermal decomposition. So we used 8.4 grams. We used 8.4 grams of magnesium carbonate if the entire mass of this magnesium carbonate has undergone complete thermal decomposition, meaning it has turned into magnesium oxide and carbon dioxide entirely. What is the number of moles of carbon dioxide that is produced? Now, we can observe one thing straight away, that magnesium carbonate to carbon dioxide molar ratio is 1:1. When one magnesium carbonate undergoes thermal decomposition, one carbon dioxide gets formed. So if you know the magnesium carbonate number of moles, we will be able to calculate the number of moles of carbon dioxide that is produced. So if you are considering magnesium carbonate, we can first find out the number of moles of magnesium carbonate, which can easily be done because we are using here pure magnesium carbonate only. So the number of moles of magnesium carbonate can be calculated using this equation: mass divided by molar mass. So the molar mass of magnesium carbonate can be calculated. We have one magnesium is 24 in mass. We have carbon, one carbon is 12 in mass, and there are 3 oxygens. Each oxygen has atomic mass of 16, and there are 3 of them, so 16 into 3 is 48. So if you add all of them together, it's going to be 84 grams per mole is going to be the molar mass of magnesium carbonate. So the mass that we used was 8.4 grams, and the molar mass is 84 grams per mole. So we can see again units cancel off perfectly, and 8.4 divided by 84 is 1/10, which is 0.1 moles. So per mole has gone up the division line, turned into mole. So this is 0.1 mole is going to be the answer for magnesium carbonate number of moles. But in the previous equation we saw, when it comes to magnesium carbonate to carbon dioxide molar ratio, that happens to be 1:1. Magnesium carbonate to carbon dioxide molar ratio is 1:1. So if you have 0.1 moles of magnesium carbonate undergoing thermal decomposition fully, you will form 0.1 moles of carbon dioxide as well. So the answer for the question that is asked here, they're asking how many moles of carbon dioxide will be produced. It will be 0.1 moles. 0.1 moles of carbon dioxide will be produced. In the next question, what is the volume that carbon dioxide gas occupies at standard temperature and pressure conditions? Now, if you take a look at this question, they say the room temperature, we'll call it T1. They also give us the volume that was collected, we'll call it V1. And we will have to find the partial pressure of oxygen, which is going to be, let's say, known as PO2, which is basically our P1, right? So let's find these values first. In the question, it says the atmospheric pressure was 1 atm and the temperature was 27 degrees Celsius. Volume that was collected was 2.37 decimeters cube, and we have the saturated vapor pressure at that temperature, which is 26.7 mercury millimeters. So students, we will first write down our volume. 2.37 decimeters cube was the volume that was collected. 2.37 decimeters cube. Temperature was 27 degrees Celsius, which means if you convert into Kelvin, 273 plus 27 is going to be 300 degrees or 300 Kelvin. 300 Kelvin. And let's say P1 is equal to partial pressure of oxygen. So we do know by carrying out quite a few calculations, when it comes to collecting gas over water, you will have the saturated vapor pressure of water as well as the partial pressure of that particular gas contributing to the overall pressure. So the overall pressure of the system, as mentioned in the question, is going to be the atmospheric pressure, which is 1 atm. So then, students, our pressure, overall pressure, or P total of the system is based on mainly two pressures, which is the partial pressure of oxygen as well as saturated vapor pressure of water at that temperature. And saturated vapor pressure of water is known to us, partial overall pressure of the system is known to us. So partial pressure of oxygen can be calculated by taking P total and subtracting the saturated vapor pressure of water. So saturated vapor pressure of water is given to us in this question. It is 26.7 mercury millimeters, 26.7, 760 mercury millimeters minus 26.7 mercury millimeters is going to be our partial pressure of oxygen. So it's going to be 3 here and 3 here, 733 mercury millimeters. So students, by now we have calculated the partial pressure of water as well. So we have calculated P1 as well. 733.3 mercury millimeters. So it is time for us to move on ahead and apply the combined gas law equation, which is P1 V1 divided by T1. Now P1 V1 T1 were our laboratory conditions. Our partial pressure of oxygen multiplied by the volume of oxygen gas we collected divided by the temperature at which we conducted this experiment. And then we have P2, V2 and T2. Now P2 is the standard pressure, which is 1 atm. T2 is the standard temperature, which is 0 degrees Celsius or 273 Kelvin. And V2 is going to be the volume of carbon dioxide gas. Actually, I continuously wrote oxygen because we were doing oxygen calculation, students, but over here we are dealing with carbon dioxide. My apologies. So this has to be carbon dioxide. So volume of carbon dioxide gas, not oxygen gas, and what we calculate over here is the partial pressure of carbon dioxide, not oxygen, students. So just to repeat myself one more time because this could create confusion otherwise. So in this case, we are not dealing with oxygen volume, we are dealing with carbon dioxide volume and carbon dioxide gas alone. So what we measured here is the carbon dioxide partial pressure. And we collected carbon dioxide gas over water. So therefore, we had in the container carbon dioxide gas as well as water. So these two gases together is what produces this 1 atm total pressure. So total pressure minus the partial pressure of water is going to give us the partial pressure of carbon dioxide, right? Total pressure minus saturated vapor pressure of water is going to give us this 733 mercury 33.3 mercury millimeters partial pressure. So we calculated P1 V1 T1 and we were talking about standard conditions. So P2 represents the 1 atm standard pressure, T2 represent the 0 degrees standard temperature or 0 degrees Celsius standard temperature, or in other words 273 Kelvin temperature. And V2 is the value that we are trying to find. V2 is the volume of carbon dioxide in standard temperature and pressure conditions. So we can actually isolate V2 if you like. V2 is equal to P1 V1 divided by T1 multiplied by T2 divided by P2. 2.081 decimeters cube will be the answer you will obtain when you solve this equation. So now students, after finding out our volume of carbon dioxide gas at standard temperature and pressure conditions, we can write it down here as an answer to this question. So 2.081 decimeters cube of a volume would be acquired by the carbon dioxide that was collected in normal laboratory conditions. So normal laboratory conditions, carbon dioxide volume was 2.37 decimeters cube, but the same amount of carbon dioxide moles will only occupy 2.081 decimeters cube of a volume when we measure the volume of carbon dioxide gas under standard temperature and pressure conditions. So the answer to this question is 2.081 decimeters cube. 2.081 decimeters cube. What is the experimental molar volume of carbon dioxide at STP? So students, earlier on we calculated that the overall number of carbon dioxide moles that were produced, CO2 number of moles were 0.1. Right, so we calculate the number of moles of carbon dioxide that were produced in a previous step of this same question was 0.1 carbon dioxide moles. And then later on, we realize that 0.1 moles of CO2 gas occupies a volume of 2.081 decimeters cube at STP. So at STP, standard temperature and pressure conditions, 0.1 moles of carbon dioxide occupies 2.081 decimeters cube. So then students, if you know that 0.1 moles of carbon dioxide has a volume of 2.081 decimeters cube, can you tell me what will be the volume of 1 mole of carbon dioxide? Quite simple. And this volume was calculated at standard temperature and pressure conditions. So therefore, we can say 0.081 decimeters cube divided by 0.1 mole, and we want to find out the volume of 1 mole of carbon dioxide, so we can multiply it with 1 mole here. So what will be the volume then? 20.81 decimeters cube. So this will be the volume of 1 mole of carbon dioxide at STP. So we can write that volume of 1 mole of CO2 gas at STP, standard temperature and pressure conditions, is going to be 20.81 decimeters cube. Here we observe the answer directly in decimeters cube. So you can write the answer. Therefore, molar volume. So when you write molar volume, especially standard molar volume or molar volume of CO2. So it is understood whenever you write molar volume that it is measured at standard temperature and pressure conditions. So therefore you don't need to mention it once more. So the molar volume that we calculated is 20.81 decimeters cube per mole. For a single mole, the volume of carbon dioxide is 20.81 decimeters cube. So this is the molar volume of carbon dioxide. So students, after coming to this point, you would understand that the molar volume that we have calculated is a bit of a deviation from the molar volume or standard molar volume of a gas that we are currently aware of, which is the 22.414 decimeters cube per mole molar volume. So here we can see the molar volume of carbon dioxide is less. So the calculated molar volume of carbon dioxide is less. I want you to make that observation here as well. So what is the molar volume that we calculated? 20.81 decimeters cube per mole. This is the molar volume we calculated. So now let's move on to the next question. What are the reasons for the deviation of the experimental molar volume value from the actual molar volume at standard temperature and pressure conditions? Now we have seen again quite a few answers for a question similar to this. We can write that carbon dioxide deviates from ideal gas behavior we can say there are intermolecular forces of attraction between CO2 intermolecular forces of attractions at play. The setup used for gas collection. Not being completely airtight. That means that some amount of carbon dioxide can leak out, right? And we are collecting this over water. So some amount of carbon dioxide gas can dissolve in water. Errors in volume measurements. And magnesium carbonate not all of the magnesium carbonate decomposing will also be a reason. Not all the magnesium carbonate decomposed. So if you have a small amount of magnesium carbonate that is in its original form without decomposing, at that point that will introduce an error, because we assumed that the number of moles of carbon dioxide that was produced was due to the full decomposition of the mass of magnesium carbonate that we took into the experiment. So if some amount of magnesium carbonate remained as magnesium carbonate and did not undergo thermal decomposition, then it will introduce a calculation error, because when we were calculating the number of moles of carbon dioxide that was produced, we assumed that all of the magnesium carbonate underwent thermal decomposition. If some magnesium carbonate didn't undergo thermal decomposition, at that point, that will introduce an error to our calculation. So students, these are the errors that you may encounter when you are carrying out this particular experiment. Let's take a look at the third question. Nitrogen gas was obtained by thermal decomposition of ammonium dichromate. A student was able to collect 1 decimeters cube of nitrogen on water by thermal decomposition of 9.71 grams of ammonium dichromate completely. So the room temperature was 30 degrees Celsius, the atmospheric pressure was 760 mercury millimeters, and the saturated vapor pressure of water at 30 degrees Celsius is 25 mercury millimeters. Now write the balanced chemical equation for the thermal decomposition of ammonium dichromate. So students, the thermal decomposition reaction is going to be this. So we have ammonium dichromate Cr2O7 undergoing decomposition to form nitrogen gas, chromium oxide Cr2O3, and water. We can balance this reaction off by adding 4 water molecules there, and this is a solid. Nitrogen is produced as a gas, chromium oxide is a solid, and this is going to be produced as a gas when you are carrying out this thermal decomposition reaction. So over here, students, we have chromium oxide solid. We have ammonium dichromate solid here, and here we have chromium oxide solid. So ammonium dichromate, students, is a orange color solid, whereas chromium oxide is a green color solid. So when you are carrying out this reaction, you will observe a color change of the solid from orange to green. So orange color ammonium dichromate will convert into green color chromium oxide. It will not be this particular green, students. However, you will see a transition in color from orange to green. So this is the balanced equation for the decomposition of ammonium dichromate producing nitrogen. What is the number of moles of nitrogen gas that is produced? So students, the 9.71 grams of ammonium dichromate that was used has reacted completely here. So that would mean if you know the balanced chemical equation of this particular reaction, we can determine the number of moles of nitrogen gas that is produced. So we have the equation NH4 or ammonium dichromate reacts to produce nitrogen gas along with chromium oxide and water. And the reaction ratio between the ammonium dichromate and nitrogen gas is 1:1. Ammonium dichromate to nitrogen gas, molar ratio is 1:1. So students, if you know the ratio between ammonium dichromate and nitrogen, we can find out the ammonium dichromate number of moles first, and then that would lead us to finding out the number of moles of nitrogen gas that is produced. So we can find out the number of moles of ammonium dichromate using this simple equation: mass of the substance divided by the molar mass of that substance. So we need to know the number of moles using this particular equation. We already know the mass of the substance, which is 9.71 grams. We need to know the molar mass of the substance. So let's calculate the molar mass of this ammonium dichromate that we have over here. So we have ammonium ions. There are 2 ammonium ions. We'll directly take ammonium ions as one single unit. So there are 2 of them, right? So one ammonium ion or one nitrogen is going to be 14 plus 4 hydrogens. Each hydrogen is going to be 1. So 14 plus 4 is going to be 18. 14 plus 4 is going to be 18. 18 into 2 is 36. And then we have chromium. There are 2 of them. Each chromium is 52. So this is 104. We have oxygens as well. There are 7 oxygens. Each oxygen is 16. So 6 into 7 is 42. And 7 plus 4 is going to be 11. So we can add all of them together. It's going to be 12 here and 5 here and 2 here. 252 would be the mass of ammonium dichromate. So if you consider its molar mass, it's going to be 252 grams per mole. You can see grams cancel off, and if you divide 9.71 by 252, you get to the answer 0.03853 as the answer. 0.03853 is going to be the answer. This is going to be coming, the unit is going to be moles, MOL. So this is the answer for the first question, 0.03853. So if you know the number of moles of ammonium dichromate, since this ratio is the same, dichromate to nitrogen gas ratio is the same, we can write amount of N2 gas produced is going to be equal to 0.03853 moles. Or you can keep it to 0.0385 as well. So this is the answer to the question that is asked. Calculate the volume of nitrogen gas that will be observed in standard temperature and pressure. Now students, according to the question, we have collected 1 decimeters cube volume of the nitrogen gas. So volume is 1 decimeters cube, We'll call it volume 1, V1. And the temperature at that point was exactly 30 degrees Celsius, which can be written in Kelvin. So 273 plus 30 is going to be 303 Kelvin. And the pressure, let's say P1, is not directly mentioned to us. The room temperature was given as 760 mercury millimeters, but we do not know the pressure of just the nitrogen gas. This is because, students, although the question says the pressure, atmospheric pressure is 760 mercury millimeters, it also says nitrogen gas was collected over water. That would mean in this area there will be liquid water, and in this area where nitrogen gas is collected, you will have gaseous water, or we say water vapor. And after a while, this entire region is going to be saturated with water vapor. So for each temperature, there will be a specific saturated vapor pressure. For each temperature, there will be a specific saturated vapor pressure. So if you know the vapor pressure of just this water, then you will be able to find out the partial pressure of nitrogen gas. So students, if you call the pressure, overall pressure over here is P total, we'll call it P total. That P total is there due to partial pressure of the nitrogen gas as well as saturated vapor pressure of water. Saturated vapor pressure of water. So P total is the atmospheric pressure, right? They have mentioned that in the question. So this is going to be 760 millimeters mercury. And we do not know nitrogen's partial pressure, but we do know the saturated vapor pressure of water at 30 degrees Celsius. And how do we know that? Because in this question, it is mentioned. It is mentioned that saturated vapor pressure of water at 30 degrees Celsius is 25 mercury millimeters. So then, students, if you know it is exactly 25 mercury millimeters, we can substitute that value here. And when you do that, you will be able to find out the partial pressure of just the nitrogen gas. It is going to be 760 minus 25 mercury millimeters. $735 is going to be the answer. 735 mercury millimeters. So now we have found out the partial pressure of just the nitrogen gas. We can call it P1, which happens to be 735 mercury millimeters. It is time for us to find the volume of this nitrogen gas if the conditions were different to what is mentioned here. So this nitrogen gas occupied a volume of 1 decimeters cube at 30 degrees Celsius and 735 mercury millimeter pressure. But the question asks us, at standard temperature pressure conditions, what will be its volume? We call that volume V2. That's what is unknown to us. And the pressure, the standard pressure is going to be 760 mercury millimeters. And standard temperature, we'll say T2, is 273 Kelvin or 0 degrees Celsius. So we can now use combined gas law equation where P1 V1 divided by T1 is equal to P2 V2 divided by T2. When substituting values to this equation, we can substitute pressure values in mercury millimeters without converting them into SI units, because as long as you use the same unit on either side for each of these different pressure volume measurements, you are going to be okay, and you will be able to obtain an accurate answer with a substitution like that. But if you substitute the pressure in one location, or let's say P1 pressure in pascals and P2 pressure in mercury millimeters, that is going to be wrong. If you substitute both values in Pascal, it is all right. If you substitute both values in mercury millimeters, then again, that will also be correct. So we will be substituting both of these values in mercury millimeters. So P1 was 735 mercury millimeters, and the volume V1 was 1 decimeters cube divided by T1, which happens to be 303 Kelvin. P2 is 760 mercury millimeters mercury, and V2 happens to be the volume that we want to find in this question. So we need to find V2. That's why we are doing this calculation. And T2 is 273 Kelvin. And you can see what I mentioned earlier about how the unit doesn't matter as long as you substitute both the units and the same value. But when it comes to temperature, of course, students, you are supposed to use Kelvin. Then you can see mercury millimeters cancel off, and your final answer is going to be obtained in decimeters cube. You can see decimeters cube is the only unit that is remaining. So now let's write the answer. V2 is equal to 0.8713 decimeters cube. So the answer is 0.8713 decimeters cube. So now, students, after finding out the answer, we can write it here, 0.8713 decimeters cube. The answer would be 0.8713 decimeters cube. This is going to be our answer. Calculate the molar volume of nitrogen at standard temperature and pressure conditions. So, students, we already know the number of moles of nitrogen gas that was produced. We calculated it earlier. Number of moles of nitrogen gas, we calculated it earlier. We can take a look at the value again. 0.03853. 0.03853 moles. So, and then later on we found the volume of this amount of nitrogen gas at standard temperature and pressure conditions in the previous part, right? In this part of the question, the volume was 0.8713 decimeters cube. 0.8713 decimeters cube. So, students, molar volume, we say VMOL, in short for molar volume, is equal to volume divided by number of moles. So volume over here is 0.0385 moles. Sorry, the volume should be written first. The number that I just wrote is the number of moles. So the volume is 0.8713 decimeters cube divided by the number of moles, 0.03853 moles. And when you do that, you will get to the answer 22.61 decimeters cube per mole. So when you solve it, students, this is the answer that you're going to get to. You can employ a simple method like this. If you know the volume of the gas, if you know the number of moles, you can just divide the volume by the number of moles. You get to the volume of a single mole, a simple mathematical relationship here. So if you know the volume of the gas and how many number of moles are producing that volume, then if you divide the volume by the number of moles, you get the molar volume of the gas. So the molar volume of the gas is going to be 22.61 decimeters cube per mole. So according to our calculations, when it comes to this particular question, nitrogen molar volume is equal to 22.61 decimeters cube per mole. So this is the answer to our question. So students, after doing this, we can write down the answer here. 22.61 decimeters cube per mole. So students, we conclude our question discussion that is revolving around experiment number 5. I hope by now you have developed a good enough understanding about the theory parts revolving around this particular experiment. With that, students, we can now move on out of the classroom and into the next experiment. I will see you again in experiment number 6.